Hello there and welcome to Life Beyond Seen, where curiosity gets cozy, science takes its shoes off at the door, and the strangest parts of natural history are allowed to settle down beside us for the evening. Tonight we are drifting far away from the world we know. Not upward into space this time, and not forward into some distant future, but backward, far backward. So far back that there are no forests, no birds, no dinosaurs, no mammals, no flowers, no buzzing insects, no grass underfoot, and no familiar shorelines filled with shells, crabs or seaweed. We are going to a time when Earth was still learning how to make animals large, fast, strange, and occasionally rather alarming. Our subject tonight is Anomalocaris, one of the most famous predators of the Cambrian seas, and a creature that looks as though nature designed it during a particularly experimental afternoon. It had a long, flexible body with swimming flaps along the sides. It had large eyes that would have been excellent tools for spotting movement in the water. It had two grasping limbs at the front of its head, curved and spiny, like a pair of jointed feeding arms reaching ahead of the body. And it had a round mouth made of hard plates, arranged in a ring, giving it the appearance of something between a pineapple slice, a camera shutter, and a very serious warning from the ancient ocean. Anomalocaris is not a dinosaur. It is not a fish. It is not a squid. It is not a shrimp, although for a long time people compared it to one because, frankly, when something extinct looks unfamiliar, the human brain tends to reach for the nearest seafood item and hope for the best. It belonged to an ancient group of animals called radiodonts, early relatives of arthropods, which means it sits somewhere on the great evolutionary road that eventually leads toward creatures like insects, spiders, crabs, and lobsters. But Anomalocaris itself was not quite like any of those. It came from a world before most of the animal designs we recognise today had fully settled into place. So tonight, as you get comfortable, I want you to imagine the ocean not as it is now, with dolphins, coral reefs, sharks, whales, turtles and shoals of silver fish, but as it was more than 500 million years ago. Imagine water full of soft-bodied animals, shelled creatures, crawling things, swimming things, and odd little forms that seem to have borrowed body parts from several different dreams. Imagine a seafloor where animals are testing out legs, shells, eyes, mouths, spikes, armour, and new ways of moving. Evolution is not neat here. It is busy. It is trying many things at once. Some of them will lead to the future, some of them will vanish, and some, like Anomalocaris, will become famous long after they disappear, because fossils have a quiet way of waiting until someone finally knows how to read them. Before we go any farther, where are you listening from tonight? Are you somewhere close to the sea where the idea of ancient water feels just a little nearer? Or are you far inland, tucked away under a roof, hearing about an ocean that existed before there were mountains shaped quite like ours, before there were forests to rustle, and before anything on land could look up at the sky and have an opinion about the weather? And if you happen to know the time where you are, maybe notice it for a moment. The hour on your clock belongs to the present, of course, but tonight we're going to stretch the mind across 500 million years, which makes even a very late bedtime seem quite modest by comparison. If you find this kind of gentle science soothing, or if you enjoy falling asleep while very old creatures do their best to be both educational and slightly unsettling, I would be grateful if you liked the video and subscribed. It helps this quiet little corner reach other tired minds, other curious listeners, and anyone who has ever thought just before sleep that perhaps what they really needed was a calm explanation of a Cambrian sea predator with face claws. And really, who among us has not been there at least once? Now settle in, let your shoulders drop, let your thoughts loosen their grip on the day. The world outside your room can continue being modern for a while, with its emails, lights, traffic, kettles, messages and clocks. We are going somewhere older than all of that. Older than cities, older than bones in the usual sense, older than jaws, older than the first land plants, older than the first fish with backbones. We are going to the Cambrian period, a stretch of Earth history that began around 541 million years ago and became one of the most important turning points in the story of animal life. The Cambrian is often described as the time when animal life became suddenly more diverse and more visible in the fossil record. That does not mean animals appeared out of nowhere in a single dramatic moment, as if Earth opened a cupboard and found a full set of strange marine creatures inside. The reality is slower and more complicated. But compared with the long stretches before it, the Cambrian fossil record shows a remarkable increase in animals with hard parts, complex bodies, active movement, and new ways of feeding and defending themselves. It is a time when life in the ocean seems to become busier, sharper, and more crowded. A time when being soft, slow, and unaware may have become a much riskier lifestyle choice. And into that changing world comes Anomalocaris. The name means unlike other shrimp, or abnormal shrimp, which is a wonderfully understated label for an animal that was not actually a shrimp and did not look especially committed to being normal. The name came from the first fossils found of its front appendages, which were mistaken for the bodies of separate shrimp-like creatures. This is one of the pleasingly messy parts of paleontology. Fossils do not always arrive as complete skeletons with labels attached. They arrive broken, flattened, scattered, and incomplete. A mouth may be found without a body, a limb may be named as one animal, a body may be named as another. Then, years later, someone realizes that all these separate pieces are actually parts of the same creature, and science has to tidy up the family album. That is exactly what happened with Anomalocaris. For decades, scientists misunderstood its remains because different parts of its body were found separately and interpreted as different animals. Its front limbs were thought to be shrimp-like creatures. Its round mouth was once interpreted as something like a jellyfish. Other body parts were described separately as well. Only much later did researchers put the pieces together and recognize that these fossils belong to a large swimming predator. It is a little like finding a glove, a set of teeth, a bicycle wheel, and a raincoat in different rooms, then eventually realizing they are all part of one very confusing person. Except in this case, the person is 500 million years old and has swimming flaps. Part of what makes Anomalocaris so striking is its size. In a Cambrian ocean where many animals were only a few centimetres long, Anomalocaris could grow much larger than most of the creatures around it. Some estimates place certain forms around 0.5 metre to a metre long, depending on the species and fossil interpretation. That may not sound enormous if you're thinking in terms of whales, crocodiles, or modern sharks, but in its own world it would have been impressive. In an ocean of small animals, a creature the length of a house cat or more would not need to be the size of a bus to make an impression. It would only need to glide overhead while everything else quietly reconsidered its plans. It is useful to pause here and avoid turning Anomalocaris into a movie monster. It was not evil. It was not angry. It was not ruling the sea with a tiny villain crown, although that image is admittedly hard to resist. It was an animal doing what animals do. It moved, sensed, hunted, fed, avoided danger, and survived as best it could in the conditions of its time. But from our point of view, it represents something important. It shows that predation had become a major force in early marine ecosystems. Animals were no longer just sitting, filtering, grazing, or drifting. Some were chasing, some were grasping, some were developing armour. Some were learning in the very slow language of evolution that if the ocean now has hunters, then being harder to catch is suddenly a very sensible idea. This is one reason Anomalocaris matters. It is not famous simply because it looks strange, though it certainly does. It is famous because it helps us picture the Cambrian Ocean as an active place, full of interactions that shape the future of animal life. Predators change ecosystems. They push prey to evolve defences. They reward speed, awareness, camouflage, armour, burrowing, schooling, hiding, and anything else that improves the odds of not becoming dinner. If you have ever watched a pigeon move out of the way of a cat with surprising dignity, you have seen a tiny modern echo of this old evolutionary pressure. The details are different, of course. There were no pigeons in the Cambrian, no cats either, just ancient animals doing the earliest versions of a very old dance. Anomalocaris also reminds us how different the first complex marine worlds were from the ones we know today. Modern oceans are filled with vertebrate predators like fish, sharks, seals, dolphins, and whales. They have jaws, backbones, muscles, skeletons, teeth, and behaviours shaped by hundreds of millions of years of later evolution. The Cambrian Ocean had none of that familiar cast. It was ruled, if we can use that word gently, by animals with body plans that can feel unusual to us because many of them left no direct modern equivalents. There were trilobites crawling across the seafloor, early arthropods moving through the water, worm-like animals burrowing or creeping, sponges filtering, and many forms that still make scientists argue over where exactly they belong. The seafloor itself would have looked different too. There were no kelp forests swaying in the currents, no coral reefs like the ones we know today, filled with bright reef fish and patient sea turtles. No shells scattered from clams as we recognise them. The land was mostly bare of complex life. If you could stand on a Cambrian shore, which I do not recommend without careful time travel insurance, you would not hear birds or insects. You would not see trees. The world would feel strangely empty above the water and strangely busy below it. The main drama of life was happening in the sea. That is where Anomalocaris belongs. Not on land, not in a swamp, not on a beach, but in open water or near the seafloor, moving through a marine world full of animals that were still experimenting with the basic possibilities of being alive in a body. It likely swam by moving the flexible flaps along its sides in waves, a motion that may have helped it glide through the water with control. Its large eyes suggest that vision mattered. This is an important point, because eyes change the rules. Once an animal can see well, the world becomes filled with targets, threats, distances, motion, and opportunity. Vision lets a predator aim. It lets prey react. It turns the ocean from a place of touch and chemical signals into a place where movement at a distance can matter. Fossils from related radiodonts have shown that these animals could have had highly developed compound eyes, with many lenses. That kind of visual system would have been valuable in an ocean where locating prey was an advantage. Imagine being a small Cambrian animal, minding your own ancient business, perhaps crawling along the seafloor with no strong feelings about the future of evolution, when a large shadow passes above. It has eyes that can pick out movement. It has front limbs that can reach and grasp. It has a mouth positioned for feeding. Even if Anomalocaris was not crunching everything in sight, and modern research suggests its diet may have leaned more towards softer prey than once imagined, it would still have been a serious presence. For many years, Anomalocaris was often imagined as a trilobite crusher. The idea made sense at first glance. Trilobites were common Cambrian animals with hard exoskeletons, and some fossil trilobites show injuries that looked like bite marks. A large predator with spiny appendages and a circular mouth seemed like a good suspect. It is always tempting when you find a prehistoric wound to point at the strangest nearby creature and say, well, it was probably that one. But science has a habit of checking the details, even when the details ruin a perfectly dramatic story. More recent research has suggested that Anomalocaris canadensis may not have been well suited for crushing hard trilobite shells, and that it may have preferred softer animals. This does not make it harmless. A predator does not need crack armour to be successful. Many modern hunters specialise in softer prey, and they do quite well without treating every meal like a nut that needs opening. This makes Anomalocaris more interesting, not less. It reminds us that ancient animals were not cartoons. They had limits. Their bodies had strengths and weaknesses. Their mouth parts could only do certain things. Their limbs could grasp in certain ways. Their swimming had certain costs. Paleontology is not just the study of what looks frightening in a museum illustration. It is the study of how real bodies worked in real environments, and when we look closely, the creature becomes clearer. Not a monster, not a mistake, not a random nightmare with fins. An animal with a particular design, suited to a particular world. The world that preserved Anomalocaris for us is also worth noticing. Many of the most famous fossils come from places with exceptional preservation, including the Burgess Shale in Canada, which is famous for keeping traces of soft-bodied Cambrian animals that normally would have decayed and disappeared. This matters because most animals are not made of parts that fossilize easily. Hard shells and bones are helpful for becoming a fossil. Soft tissues are much more likely to be eaten, scattered, rotted, or erased. If we only had ordinary fossil deposits, we would know far less about Cambrian life. We might imagine the early oceans as much emptier than they were, simply because the soft animals had failed to leave good records. Sites like the Burgess Shale give us a rare look at the softer side of ancient life, although softer side is perhaps an odd phrase when one of the animals is Anomalocaris. There is something calming about this, in a strange way. The animal lived, hunted, moved through the water, and vanished from the living world hundreds of millions of years before any human existed to name it. Then, by chance, some of its remains were buried in conditions good enough to preserve them. Rock formed, continents shifted, mountains rose, ice came and went, forests appeared, dinosaurs evolved and disappeared, mammals spread, humans eventually arrived, learned to split rocks, read fossils, argue over details, revise their mistakes, and give the creature a name. Anomalocaris did not know any of this would happen. It simply lived in its sea. Yet here we are, in the modern night, speaking of it softly. That, I think, is one of the quiet pleasures of natural history. It lets us meet lives that had no connection to us in any direct personal sense, and yet are part of the same long story of life on Earth. Not a story with a planned ending or a neat ladder from simple to advanced. More like a branching record of experiments, accidents, extinctions, survivals and changes. Anomalocaris is one branch, we are another. A trilobite is another. A house spider in the corner of your room, doing very little and somehow still looking busy, is another. All of it belongs to the same planet, though not the same moment. Tonight, we are going to move carefully through that ancient world. We will begin before animals looked familiar, when the seas were full of early forms and the land was almost empty. We will look at the body of Anomalocaris piece by piece, not in a rushed museum label way, but slowly, so the creature becomes easier to picture. We will spend time with its eyes, its feeding limbs, its mouth, and its swimming body. We will visit the Cambrian ocean around it, where evolution produced animals so unusual that even specialists sometimes have to sit with them for a while. We will talk about how a predator can shape a world without needing to be huge by modern standards. We will also follow the fossil mystery, because Anomalocaris was not understood all at once. It had to be assembled in the human mind from pieces that seemed, at first, not to belong together, and eventually, though not too quickly, we will come to its disappearance. Not as a dramatic curtain drop because nature rarely works like a stage play, but as part of the long turnover of life. The rulers of one sea do not rule forever. Body plans rise, spread, change and fade. Other predators come. Other ecosystems form. The ocean keeps revising itself. Anomalocaris had its time, and then its time passed, leaving behind impressions in stone, and a very useful reminder that Earth's past is much stranger than a simple march toward the present. For now, let us stay at the edge of the Cambrian water. Imagine the surface under a quiet sky, though the continents and coastlines are not arranged as they are today. Below that surface, small animals move in the dimness. Some crawl, some drift, some burrow, some hide. Then something larger passes through. Its side flaps move in a steady wave. Its eyes scan. Its front limbs reach ahead. It is not a shark. It is not a squid. It is not anything you would expect to see in a modern aquarium, unless the aquarium had made several bold choices without consulting the staff. It is Anomalocaris, and for a while in Earth's first complex oceans, it was one of the animals that made being small a little more complicated. So let us begin there, in the water before fish, before reefs as we know them, before the sea had settled into its familiar roles. The lights of the modern world can fade for a little while. The old ocean is waiting, and something with wide eyes and grasping limbs is already moving through it. Long before the fur shark moved through the water with that slow, confident glide we recognize today, long before fish filled the seas in flashing schools, long before coral reefs became busy underwater cities, the ocean was already full of life. It was not empty. It was not simple in the way people sometimes imagine ancient life to be simple, but it was unfamiliar, very unfamiliar. If you could lower yourself gently into a Cambrian sea, wearing whatever extremely advanced and probably quite expensive time travel diving suit would be required for such a trip, you would not see a world ready-made for dolphins, tuna, turtles or seals. You would see an ocean still working out what animals could become. That is a strange thought, because we are used to oceans having a certain cast of characters. Fish are so common in our idea of the sea that it is almost difficult to imagine water without them. Say the word ocean, and the mind quickly supplies fins, tails, gills, scales, teeth, and perhaps a shark moving somewhere in the distance, because apparently the human imagination hires sharks for nearly every marine scene, whether they are needed or not. But in the early Cambrian, the familiar ocean had not yet been built. The parts were there in early forms. Movement was there. Feeding was there. Sensing was there. Defense was there. But the standard designs were not yet standard. There were animals before the Cambrian, of course. The Earth did not go from lifeless water to a crowded marine festival overnight. The period before the Cambrian, especially the Ediacaran, had its own soft-bodied creatures, many of which looked unlike anything alive today. Some were flat and quilted, some were frond-like. Some rested on the seafloor and absorbed or gathered food in ways scientists are still working to understand. These animals are important because they remind us that the Cambrian was not the first page of animal life. It was more like the moment when the handwriting becomes darker, busier, and much easier to see in the fossil record. One reason the Cambrian seems so dramatic is that many animals began making harder parts, such as shells, plates, spines, and external skeletons. Hard parts fossilize more easily than soft flesh, which is very inconsiderate of soft flesh, but quite helpful for paleontologists. Before that, many animals could live and die without leaving much behind. Imagine trying to reconstruct a whole city if only the metal door handle survived. You would know something had been there, but you would miss the curtains, the food, the furniture, the people, and probably the small emotional drama happening near the kettle. Fossils are selective. They preserve what circumstances allow. So when Cambrian rocks begin showing more hard parts and more complex forms, the record becomes clearer, and the ocean suddenly appears crowded with invention. The Cambrian period began around 541 million years ago. That number is so large that it can become almost meaningless if we say it too quickly. 541 million years, not 5 million, not 50 million, more than 500 million years. If the entire history of Earth was squeezed into a single day, humans would arrive very near the end, barely in time to look around, make some tea, and start asking difficult questions. The Cambrian would still be far back in that day, long before forests, flowers, reptiles, mammals, birds, or anything with a face you would find comforting in a pet shop. The land at this time was not a green world. There were no forests lining the coasts, no insects humming over leaves, no birds calling from branches, no mammals sniffing at the soil. Most complex life was in the sea. Land existed, of course, but it was mostly bare in the way a building site is bare before anyone has put down carpets, planted shrubs, or made poor choices with outdoor furniture. Microbial life may have coated damp places. Simple organisms lived in their own quiet ways, but the grand visible drama of animals was underwater. If you stood on a Cambrian shoreline, the silence might feel unsettling. No gulls, no crickets, no rustling grass, no frogs, no distant animal calls. The air would not carry the sound of wings or insects. The land would not yet have the busy biological texture we expect. It would be rock, sediment, water, weather, and microbial films, with the main activity hidden below the waves. To us, it might feel like an empty planet, but that would only be because we are land animals, and land animals are slightly biased about where the interesting things are happening. Below the water, things were changing quickly in evolutionary terms. Animals were moving in new ways. Some crawled across the sea floor, some burrowed into sediment, some filtered tiny particles from the water, some grazed on microbial mats, some drifted, some swam, some developed shells or spines, some grew eyes. And once eyes entered the scene, the ocean became a much more complicated place. An eye is not just a body part, it is a change in behaviour waiting to happen. A creature that can detect light and motion can find food from farther away. It can avoid danger sooner. It can move towards shelter, away from shadows, or into open water with better information than a creature relying only on touch or chemical signals. It does not need to understand what it sees. It does not need to think, "Ah, yes, a predator, how unfortunate." It only needs a nervous system that turns light into action. Move, hide, chase, turn, stop, grab. These are simple words, but in an ancient ocean they were powerful. This is one of the reasons the Cambrian seas were so important. They were not merely filled with bodies, they were filled with relationships, predator and prey, armour and grasping limbs, eyes and camouflage, burrows and searching mouths, spines and soft undersides. Once animals begin interacting in these ways, evolution becomes a kind of pressure from all directions. A shell helps if something is trying to bite or grip you. Better vision helps if food moves. Faster swimming helps if danger appears behind you, which is also true in modern life if the danger is a bus you did not hear coming. Burrowing helps if the seafloor surface becomes risky. Spines help if something tries to swallow you and immediately regrets its life choices. Before fish became common, before jaws became the famous biological tools they later became, the Cambrian Ocean already had hunters. They were not sharks, they were not barracudas, they were not the sleek predators of modern documentaries with dramatic music and suspiciously patient camera crews. Many were invertebrates, animals without backbones, and some of the most impressive belong to groups that feel strange to us now, because they do not fit neatly into everyday categories. Anomalocaris was one of these. So were its radiodont relatives. They belonged to the broader evolutionary neighbourhood of arthropods, but they were not crabs, not insects, not spiders, and not lobsters. They were earlier branches, animals from a time before those later groups became familiar. It is tempting to describe the Cambrian as a world of experiments, but that word can be misleading if we imagine evolution sitting at a workbench with a pencil tucked behind one ear. Evolution does not plan. It does not sketch a trilobite in the morning and a radiodont after lunch. It works through variation, inheritance, survival, reproduction, extinction, and time. Animals that happened to have useful traits left more descendants. Animals that did not were less successful or disappeared. The result can look creative from our point of view, but it is not creative in the human sense. It is more like a long series of practical tests carried out by living bodies in real environments. The ocean asks, "Can you survive this?" And each animal answers with its shape, behaviour and luck. Many Cambrian animals would look odd to modern eyes because they represent early versions of body plans, side branches of evolution, or entire groups that later vanished. Trilobites are among the more recognizable Cambrian animals today. partly because their fossils are common and their hard exoskeletons preserved well. They crawled along the seafloor with segmented bodies and tough outer coverings, and they came in many shapes and sizes over their long history. They are extinct now, but they lasted for an enormous span of time. In the Cambrian, they were among the animals learning how useful armour could be, when the neighbourhood suddenly included hunters. There were also worm-like animals, some with spines, some with strange mouth parts, some with body forms that make them look like brushes, tubes, or small armoured slippers. There were early mollusk-like creatures, sponge communities, small shelly fossils, and animals that are still difficult to place on the family tree. There were creatures such as Hallucigenia, with its spines and little legs, once reconstructed upside down because its body was so unusual that even trained scientists had to spend time deciding which side belonged on the floor. There was Opabinia, with 5 eyes and a long flexible proboscis ending in a grasping structure, a creature that seems almost designed to make museum visitors lean closer and whisper, "Excuse me, what exactly am I looking at?" These animals were not strange to themselves. That is worth remembering. A trilobite did not think it looked old-fashioned. Opabinia did not wake up embarrassed about having 5 eyes. Anomalocaris did not patrol the sea thinking, "I am one of the weird wonders of the Cambrian." These were ordinary animals in their own world. They were normal to the water they lived in. We are the ones arriving late, with modern expectations and a habit of comparing everything to a shrimp, a squid, or a vacuum cleaner attachment. In those seas there were early chordates too, small animals closer to the line that would eventually lead to vertebrates. Some Cambrian fossils show primitive fish-like or chordate forms, but they were not the fish-dominated world we know from later periods. The great age of fishes would come much later. Sharks, with their cartilaginous skeletons and famous teeth, were also far in the future. So when we say before fish, we should be careful. The earliest vertebrate relatives and primitive jawless fish-like animals began appearing around this broad interval. But the ocean was not yet ruled by fish in the ordinary sense. It was not a place where bony fish and sharks had taken over the roles of fast hunters and active swimmers. The top predators of the time could be animals like radiodonts, using front appendages rather than jaws, and swimming with side flaps rather than tails. That difference matters. Modern marine predators often rely on jaws. A shark bite is a very direct piece of engineering. Open mouth, expose teeth, close mouth, remove problem, or create one, depending on which side of the shark you're on. But Anomalocaris came from a world before jaws were the dominant predatory equipment. It had a round mouth made of plates, and a pair of frontal appendages that could reach out and handle prey. It did not need to resemble a shark to be effective. It belonged to a different solution, a Cambrian solution, one built from grasping limbs, vision, flexible swimming, and a body plan that looks unfamiliar because later evolution took other routes. The ocean itself would have had different textures and structures from today's seas. Without large fish, marine reptiles, whales, or modern coral reef ecosystems, the food webs were arranged differently. Many animals live close to the seafloor, where sediment, microbial mats, and small organisms provided feeding opportunities. Burrowing became more important during the Cambrian, and this changed the seafloor. Earlier seafloors may have been more heavily covered by microbial mats, but as animals dug and stirred the sediment, they altered habitats. A seafloor with burrows is not the same as a seafloor without them. It has hiding places, tunnels, disturbed layers, and new ways for oxygen and nutrients to move. Even small animals can remodel a world if enough of them keep poking holes in it. This increase in burrowing and movement also changed the fossil record. Trace fossils, such as trails and burrows, show behaviour rather than bodies. A trackway says, "Something passed here." A burrow says, "Something lived or fed here." These are not portraits, but they are evidence of action. In some ways, they are wonderfully intimate. A body fossil tells us what an animal looked like. A trace fossil tells us what it did. It moved across mud. It dug downward. It searched. It rested. It escaped. It disturbed the surface and left a line behind, not knowing that hundreds of millions of years later, a human would study that line and try to imagine the animal at the other end of it. The Cambrian seas were also changing chemically and physically. Oxygen levels, ocean chemistry, ecological interactions and evolutionary developments all played roles in the diversification of animals. There is no single simple cause that explains everything. Science is usually rude like that. We prefer one neat answer, preferably with a label and a tidy diagram. The Cambrian gives us several interacting factors instead. More oxygen may have supported more active lifestyles and larger bodies. Genetic developmental systems may have allowed animals to build more complex forms. Predator-prey relationships may have pushed the evolution of shells, spines, and mobility. Environmental changes may have opened new opportunities. All of these likely mattered in different ways. This is why the Cambrian is not just a gallery of odd fossils. It is a turning point in how animal ecosystems worked. Before this, much of animal life was soft, slow, or less easily preserved. During this interval, we see more animals with parts designed for movement, feeding, defense, and sensing. The ocean becomes more like a place of active encounters. Not always dramatic encounters, of course. Much of life is still small and repetitive. Even in the Cambrian, not everything was a chase scene. Some animals were probably doing the ancient equivalent of sitting quietly and filtering particles from the water, which is a respectable lifestyle, and one that sounds rather peaceful at bedtime. Still, the presence of larger predators changes the emotional picture for us, even if the animals themselves did not have emotions in any familiar way. We can understand, at least broadly, what it means to be hunted. We can picture the pressure that would favour armour, eyes, speed, and caution. When we look at Anomalocaris, we are not just looking at one animal. We are looking at an ecological role becoming visible. A large active hunter in a world where many animals were small. A swimmer with eyes in a sea where vision was becoming increasingly important. A predator from before the age of Jaws, showing that nature did not wait for teeth to invent danger. The absence of familiar animals also helps us appreciate how temporary our version of the ocean is. We tend to think of the natural world around us as standard. Fish belong in the sea, trees belong on land, birds belong in the sky. Insects belong absolutely everywhere, including places where one would prefer they did not. But these arrangements have histories. There was a time before forests, a time before flying insects, a time before flowering plants, a time before reefs filled with clownfish and anemones, a time before whales sang in deep water. The Cambrian reminds us that Earth has had many different versions of normal. For Anomalocaris, the normal world was one without bones as the major framework of large predators. It did not look around for sharks, because sharks did not exist. It did not chase modern fish, because they were not there. It did not glide over coral reefs full of bright colours and darting reef animals. Its sea had its own communities, its own prey, its own hiding places, its own risks. It lived in a world where the basic rules of animal life were becoming sharper. See and be seen, grab and escape, harden or hide, swim or be caught. Not all at once, not in a simple straight line, but enough that the ocean became a more active and contested place. A small Cambrian animal might have spent much of its life close to the sediment. It might have fed on tiny particles, grazed on microbial growth, or searched for scraps. It might have had a shell, spines, or a tough outer covering. It might have responded to shadows or vibrations. It did not need a brain like ours to survive. It needed enough of a nervous system to react correctly more often than not. Move away from danger, move toward food, stay still when stillness helps. Burrow when the surface becomes unsafe. These small decisions, repeated across generations, shaped bodies over time. Then above or beside that small animal, something larger could pass. Not a fish, not a shark, not a squid, a radiodont. Its body moves by waves alongside flaps, Its front appendages hang ready. Its eyes gather information. It is part of a world where predation has become a serious force. The small animal may not know what Anomalocaris is in any thinking sense, but its lineage may still be shaped by the presence of such hunters. This is how evolution works at the level of populations. Fear does not need to be conscious to leave a mark. Survival leaves the mark. One of the calmest ways to think about this ancient ocean is to remove one familiar thing at a time. Take away the sharks. Take away the bony fish. Take away the whales. Take away the sea turtles. Take away the crabs as we know them, the lobsters, the familiar shells on the beach, the kelp forests, the coral reef fish, the dolphins, the seals, the gulls overhead. Keep the water. Keep the sediment. Keep the sunlight filtering down. Keep small animals moving through the layers. Keep the need to eat and avoid being eaten. Keep the slow work of evolution. What remains is not empty. It is simply older than our usual imagination. This older ocean is where Anomalocaris makes sense. In a modern sea, it would look out of place, like someone attending a formal dinner wearing swimming flaps and a circular mouth. But in the Cambrian, it was not out of place. It was one of the animals that belonged. Its body was suited to its surroundings. Its strangeness is partly a trick of distance. We are separated from it by so much time that its ordinary features have become extraordinary to us. That distance can be useful. It lets us see the present more clearly. The animals we call normal are only normal because they are alive now, or because we have seen them often enough. A crab looks normal until you describe it honestly. A spider looks normal only because we have made peace with the fact that 8-legged silk-making household ceiling residents exist. A squid is a soft-bodied animal with arms around its mouth, excellent eyes, colour-changing skin, and a talent for vanishing into ink, which is not exactly a conservative design. Life has always been strange. The Cambrian simply shows us strangeness before familiarity had time to cover it with habit. So before we picture Anomalocaris in detail, it helps to hold this world around it. The animal did not appear in an empty blue space like a logo on a screen. It moved through a living sea filled with other bodies, other strategies, other ancient problems. It belonged to a period when the fossil record shows many major animal groups becoming more visible, when hard parts became more common, when ecological relationships became more intense, and when life in the ocean began to look more active in ways we can still recognise. Not modern, but active. Not familiar, but alive. The first great predators did not need to be sharks. They did not need jaws lined with replaceable teeth. They did not need skeletons of bone or sleek tails or the clean outline of a tuna. They could be stranger than that. They could have front limbs like curved tools, eyes suited for tracking movement, and a mouth that looks as though it was assembled from plates by a very focused committee. They could swim through a sea where being large, alert and mobile was enough to make them powerful. And with that world in place, the creature itself can come closer. Not as a vague ancient monster, and not as a simple oddity from a fossil display, but as a real animal built from real parts. Its body was long and flexible. Its side flaps moved it through the water. Its head carried the equipment of a hunter. The more carefully we look, the less it seems like a random collection of strange features, and the more it becomes a working design from a time before the ocean had anything familiar to compare it with. Now that the familiar ocean has been gently taken away, with its fish, sharks, reefs, whales, and all the modern creatures we usually invite into our imagination, we can let the Cambrian Sea come into focus on its own terms. And once we do that, Anomalocaris begins to make more sense. Not complete sense, perhaps. Let us not pretend too much. Even after more than a century of study, it still has the air of an animal assembled from parts that were not expected to share an address. But it makes the kind of sense that living things make when you stop asking them to look familiar and begin asking what their bodies were built to do. At first glance, Anomalocaris looks like something that has drifted in from a dream that was interrupted halfway through. It has the long body of a swimmer, but not the tail of a fish. It has side flaps, not fins as we usually picture them. It has large eyes, not tucked modestly into a skull, because there is no skull in the way we would expect. It has two curved appendages at the front reaching forward like flexible tools, and then there is the mouth, a round mouth, a plated mouth, a mouth that does not open with an upper jaw and a lower jaw, because jaws had not yet become the dominant feeding equipment of the sea. Instead, it sits there like a ring of hard pieces, arranged around an opening, giving the creature a face that feels both practical and deeply impolite. This is part of why Anomalocaris has become so memorable. Many extinct animals are interesting because they are huge or fierce or close relatives of something we know. Anomalocaris is interesting because it seems to come from a different draft of animal life. It is not merely an old version of a modern predator. It is a reminder that the ocean once tried designs that do not have a tidy modern equivalent. When you look at it, you cannot simply say, "Ah, an early shark," and move on with your evening. It asks for a little more attention than that. Very inconsiderate, really, for a creature that is supposed to help us relax. The body itself was long and flexible, built for swimming rather than crawling. Along the sides were repeated flaps, arranged in pairs, and these would have moved in waves to push the animal through the water. This is not the flick of a fishtail, and it is not the pulsing bell of a jellyfish. It is a different kind of motion, one that may have allowed the animal to glide, steer, and adjust its position with surprising control. Picture a ribbon of movement passing down the sides of the body, each flap contributing to the next, so the whole animal moves not with a single thrust, but with a coordinated undulation. It is not difficult to imagine it travelling through the water with a steady, slightly alien grace. That word, alien, comes up often with Cambrian animals, though of course they were not alien at all. They were entirely Earth-made. Every strange edge and flap and plate belonged to this planet. The problem is not that Anomalocaris came from somewhere else. The problem is that it came from here before here looked like home. It is older than our categories. We call it alien-looking because our minds are trained by the living world around us, and the living world around us is the result of many later changes. If Anomalocaris had survived into modern oceans, if it were something diverse or drifting above reefs, perhaps we would find it no stranger than a squid or a manta ray. Children would have plastic Anomalocaris toys in beach shops. Someone would put one on a mug. There would be documentaries with dramatic music and at least one presenter whispering, "There it is," as if the animal had been waiting politely for its close-up. But Anomalocaris did not survive into our seas. It belongs to a much earlier marine world, and that makes its appearance feel startling. At the front of the body were the two appendages that made such an impression on early fossil researchers. They were segmented, curved and lined with spines. These were not legs for walking. They were not antennae in the simple sense. They were feeding limbs positioned ahead of the mouth, able to reach, flex and help capture prey. In life they may have swept forward or downward, grasping animals in the water column or handling soft-bodied prey. They are among the clearest clues that Anomalocaris was not a passive drifter. It was equipped to interact with moving food in a direct way. Imagine them as a pair of jointed arms, though not arms like ours. They were more like curved, spiny, flexible capture tools. Each one was divided into sections, and those sections carried projections that could help trap or hold prey. If you were a small Cambrian animal, especially one without heavy armour, the sight of those appendages coming toward you would not have been an encouraging development. Not that you would have paused to describe your feelings in a journal. Most likely you would have tried to move away, assuming your nervous system was up to the job. The Cambrian Sea was not offering much in the way of formal warnings. The eyes add another important detail. Anomalocaris was not just reaching blindly through the water. Fossils from related material, including Anomalocaris from the Emu Bay Shale in Australia, show that these animals could have large compound eyes with many lenses. Compound eyes are familiar today from arthropods such as insects and crustaceans, though of course Anomalocaris came from a much earlier branch of that wider evolutionary neighbourhood. The important thing is that vision was clearly part of the equipment. Large eyes suggest an animal that used sight to navigate and find food. It was not simply bumping into lunch by accident, which is a strategy, but not always an elegant one. There is something especially striking about good vision in such an ancient animal. We often think of early life as dim, slow and simple, as though ancient creatures were moving through the water in a kind of biological fog, but Anomalocaris pushes against that idea. It had eyes, it had swimming ability, it had grasping appendages, it had a body organised for active life. It was part of a world where seeing and moving mattered. That means prey animals too were under pressure. If a predator can see you, then hiding becomes useful. Armour becomes useful. Burrowing becomes useful. Being transparent, spiny, quick, small, flat or difficult to handle all become reasonable options. The development of eyes does not just improve one animal, it changes the whole conversation. Then we come back, inevitably, to the mouth. The mouth of Anomalocaris is one of those features that makes the creature hard to forget. It is often described as a circular or disc-like oral cone, made from hard plates arranged around the opening. Older illustrations sometimes made it look like a perfect ring of crushing teeth, the kind of mouth that could bite straight through anything foolish enough to be nearby. That image is dramatic, and very useful if one is trying to make a prehistoric animal seem like the villain in a low-budget underwater thriller. But the real animal was more specific than that, and more interesting. Unlike modern jawed predators, Anomalocaris did not have jaws that hinged open and shut. Its mouth parts were arranged radially around a central opening. This means it fed with a structure quite unlike the bite of a shark, the snap of a crocodile, or the chewing mouth of a mammal. The plates of the oral cone may have helped grip, process, or draw in food, but researchers have debated exactly how effective the mouth would have been against hard prey. For a long time, Anomalocaris was imagined as a powerful trilobite crusher, partly because trilobites were common, and partly because some trilobite fossils show injuries. It made a simple picture. Hard-shelled prey below, large strange predator above, case closed. Paleontology, however, often enjoys reopening cases just when everyone has become comfortable. More recent work has questioned whether Anomalocaris canadensis was well suited to biting through hard trilobite shells. Some studies suggest its frontal appendages and mouth were better adapted for catching and feeding on softer animals, especially active prey in the water, rather than heavily armoured animals on the seafloor. This does not make Anomalocaris gentle. A predator specialising in softer prey is still a predator. A heron does not need to crush a turtle to be taken seriously by a fish. A spider does not need to bite through a helmet to be effective. Bodies evolve for particular feeding problems, not for impressing museum gift shops. This is a useful correction because it brings Anomalocaris closer to a real animal and farther from a monster. A monster can do anything the story requires. A real animal has mechanics. Its limbs bend only so far. Its mouth can handle some materials better than others. Its eyes work under certain light conditions. Its swimming has strengths and limits. Its prey choices are shaped by what it can catch, hold, and swallow without damaging itself. Once we think this way, the animal becomes less like a random nightmare and more like a working piece of Cambrian biology. Still odd, yes, but odd with a job. The head region must have been an important centre of action. Eyes watching, appendages reaching, mouth waiting behind them. In many modern animals, the head is where sensing and feeding equipment gather together, and Anomalocaris shows an early version of that theme. The front end of the body is not just the part that arrives first, it is the part that finds, judges and handles the world. For a swimmer in the Cambrian Sea, that mattered. If prey was ahead, the animal needed to detect it, approach it, position those appendages, and bring food toward the mouth. There is nothing casual about that arrangement. The rest of the body supported this front-end lifestyle. The side flaps provided movement. The tail fan, in some reconstructions, may have helped with steering or stability. The body likely carried structures associated with breathing, including blade-like features that in radiodonts are interpreted as gill structures. Since these animals did not have backbones or lungs, they were using a very different arrangement from the animals we know best. But the underlying problem was familiar. Get oxygen, move through the environment, find food, avoid damage, reproduce, keep the body working long enough to leave descendants. Life is creative in its forms, but its basic chores are stubbornly repetitive. Size also contributed to its presence. Anomalocaris was large compared with many animals around it. Its exact size depends on species and fossil interpretation, and estimates have changed as researchers have studied the proportions of its parts more carefully. Even so, it remains one of the largest animals known from Cambrian fossil communities such as the Burgess Shale. In an ocean where many animals were small, being tens of centimetres long was enough to be impressive. Size is always relative. A house cat does not seem enormous in your living room unless you are a mouse. Then the situation has a very different tone. In the Cambrian context, a swimming predator of that size would have been an important presence, not because it was gigantic by all standards, but because it occupied a role that made it ecologically powerful. It could move through the water, it could see, it could capture prey. It could operate above or near communities of smaller animals. That combination would have set it apart. We should be careful with the word ruled, because ecosystems are not kingdoms in the simple sense. No creature sits on a throne issuing decrees about sediment management, but Anomalocaris was likely among the top predators of its environment, and that is close enough to ruling for a bedtime story about ancient seas, provided we imagine the crown as very damp and difficult to wear. Part of its strange look comes from the absence of features we expect. No obvious face with cheeks or a jawline. No familiar fish body tapering to a tail fin. No paired fins like a modern vertebrate. No shell like a crab. No tentacles like a squid. No neat insect-like body divided into the kind of segments we see in later arthropods. It is not that Anomalocaris lacks organization. It is highly organized. It is just organized according to rules that are not the rules we automatically recognize. The eyes sit forward. The appendages project from the front. The mouth is underneath or behind them. The flaps repeat along the trunk. The whole animal is coherent, but not familiar. This is where the dreamlike quality comes from. Dreams often combine recognizable parts in unfamiliar arrangements. An eye is recognizable. A swimming body is recognizable. Grasping limbs are recognizable. A mouth is very recognizable, especially if it seems likely to use you as part of its evening plans. But Anomalocaris arranges these things in a way that does not match our usual templates. The result feels surreal, even though it was not surreal at all. It was practical. The ancient ocean did not reward strangeness for strangeness' sake. It rewarded working bodies. The fossil record, however, gives us this body in fragments, flattened in rock and interpreted through careful comparison. We do not have a living Anomalocaris in an aquarium tank, slowly bumping into the glass while scientists take notes and argue over whether it looks more like a shrimp or a decorative vacuum attachment. We have fossils. Fossils are evidence, but they are also puzzles. Soft-bodied animals are especially difficult because their forms can be distorted during burial and preservation. Parts may separate. Structures may flatten. Details may be lost. This is why reconstructions change over time. Science is not embarrassed by that, or at least it should not be. Changing a reconstruction when new evidence appears is not failure. It is the work. The early confusion around Anomalocaris makes perfect sense when you think about the animal's appearance. If you found only one frontal appendage flattened in stone, would you immediately conclude it was the feeding limb of a large swimming radiodont? Probably not. You might think it was the body of a shrimp-like animal, as early researchers did. If you found the mouth separately, Would you know it belonged to the same creature? Again, probably not. It might look like a jellyfish or some other circular organism. When the parts are separated, each one tells an incomplete story. Only when enough fossils are compared does the larger animal emerge. Anomalocaris was not just fossilized in stone, it had to be assembled in scientific understanding. There is something almost humorous about this, though not in a way that mocks the scientists involved. They were working with strange material and limited context. The Cambrian was full of forms that challenged expectations. If anything, the history of Anomalocaris shows how difficult it is to interpret life from deep time. Nature does not always label the front end. Fossils do not politely say, "This is a mouth," or "This is part of a larger animal. Please do not name me separately." Paleontologists have to compare shapes, positions, preservation, related fossils, and the anatomy of living animals. Sometimes they get it wrong, then later they get it less wrong. That is progress, which is often less tidy than we like, but more honest. When we picture Anomalocaris alive, it helps to remember that its body was not a fossil diagram. It was a moving animal with tissues, surfaces, and behaviour. The flaps would have shifted as it swam. The appendages may have flexed and curled. The eyes would have caught light. The mouth would have opened to take in food. The body may have cast a shadow over the seafloor. Smaller animals may have reacted to its movement. Sediment may have stirred beneath it. Its world was not a still display case. It was water, light, current, hunger, motion, and contact. The animal's appearance also tells us about one of the great themes of early animal evolution, the assembly of active bodies. A passive animal can survive by staying in place and filtering food if conditions allow. Many still do. Sponges have been quietly making a living for a very long time without needing to chase anyone, which is admirable. But active predation requires coordination. Sensors, movement, feeding structures, digestion and behaviour have to work together. Anomalocaris shows us that by the Cambrian, such coordination had already become sophisticated. Not modern in style, but effective in its own setting. This is why it holds our attention. It is not only strange looking, it is evidence of an early ocean where animals were already locked into complex relationships. The large eyes are not decoration. The grasping appendages are not random ornaments. The mouth is not a spooky detail added for dramatic effect. Each feature belongs to the practical problem of being a predator in a sea full of possible meals and possible competition. Even the parts that look most dreamlike were shaped by real pressures. Still, it is difficult not to smile a little at the face, if we can call it a face. Humans are very face-focused animals. We search for faces in clouds, rocks, electrical outlets, and the front of cars. Anomalocaris gives us just enough facial information to unsettle that instinct. 2 large eyes, yes. A mouth, yes. But not arranged in a comforting mammal way. It is a face from before. Faces became familiar. The eyes do not soften it. The mouth does not smile. The appendages frame the front like tools rather than expressions. It is not frightening in a deliberate sense, but it is certainly not cuddly. There is no plush version of Anomalocaris that would not need a little explanation before bedtime, though I suspect one exists somewhere, because humans are wonderfully committed to making soft toys out of absolutely anything. And yet, the longer we sit with the animal, the less monstrous it becomes. The unfamiliar becomes specific. The side flaps are for swimming, the appendages are for capturing prey, the eyes are for seeing, the oral cone is for feeding. The body is long because it moves through water. The parts are not random, they are not decorative, they are not symbols of ancient weirdness, they are anatomy. This is where the real wonder sits, not in calling the creature bizarre and leaving it there, but in understanding that its bizarre appearance was normal once. For millions of years, animals like Anomalocaris and other radiodonts moved through ancient seas as part of functioning ecosystems. They were born, grew, fed, avoided harm and died. Their bodies made sense to the demands around them. The fact that we find them strange is a measure of how much the world has changed since then. So, when we say the creature looked like a dream had teeth, we should add that the dream was built from working parts. It was not a fantasy. It was not a mistake. It was a predator from a time before Jaws, before sharks, before the familiar sea. Its teeth, if we use that word loosely for the plated mouthparts, were not teeth like ours or like a shark's. Its claws were not claws in the crab or bird sense. Its fins were not fish fins. Everything about it asks us to step outside modern expectations and meet the Cambrian Ocean on its own terms. And once we do, Anomalocaris becomes easier to follow through the water. The animal no longer floats in the mind as a strange fossil celebrity. It becomes a swimmer, a hunter, a body using vision, movement and grasping limbs in a sea filled with smaller animals. It is still alien looking, yes, but now the strangeness has a purpose. The dream has anatomy. The teeth have a job. And just ahead of that round mouth, the two spiny appendages wait like the first great tools of predation in an ocean that was still deciding what danger could look like. Anomalocaris did not move through the Cambrian Sea like a fish. That is one of the first things to let go of. It did not swing a tail from side to side in the familiar way. It did not slice through the water with paired fins and a neat streamlined body like a tuna. It did not cruise like a shark, with a stiff, confident shape and a mouth full of replaceable teeth. It belonged to an older style of swimming, a style from a time when the ocean had not yet settled on the designs that now seem obvious to us. Along the sides of its body were flaps. Not wings in the bird sense, of course. There were no feathers, no bones, no graceful landing on a branch, and certainly no little Cambrian airport where it could complain about delays. But the flaps acted like swimming surfaces, broad, flexible structures arranged along the body in repeated pairs. When Anomalocaris moved, these flaps likely undulated in waves, passing motion down the body and pushing the animal through the water. It was a swimmer with many moving surfaces, not one big tail. Its body did not simply lunge forward. It worked in sections, each flap contributing to the movement, each wave helping the creature travel through its world. This is why calling them swimming wings feels useful, even if it is not a technical description. The flaps were not wings for air. They were wings for water. They gave the animal lift, control and propulsion in a sea that was full of smaller bodies, drifting particles, currents, and sudden chances to feed. Imagine something long and flexible moving above the seafloor, its side flaps shifting in a smooth sequence. The front of the body points forward. The eyes watch. The appendages are held ready. Behind them, the flaps ripple. The animal advances not with the sharp flick of a fish, but with a controlled motion that makes it seem both calm and dangerous. There is a quiet lesson here. Early predators did not need to look like modern predators to be effective. We are used to thinking of speed and hunting in terms of fishtails, shark bodies, squid jets, and seal muscles. But Anomalocaris came from a different engineering tradition. Its body was built before the ocean had many of the later options. There were no sharks to imitate. No large bony fish setting the standard for marine speed. No dolphins making everything look effortless and slightly smug. Anomalocaris had its own solution. Side flaps, a flexible trunk, a tail fan for control, front appendages held like tools, large eyes to guide the whole operation. The body shape of Anomalocaris tells us that it was not built for sitting still. Many Cambrian animals lived on or near the seafloor, crawling, burrowing, clinging, grazing or filtering. That kind of life can be very successful. It has worked for sponges, worms, shell-bearing animals, and all sorts of creatures that have no interest in high-speed drama. But Anomalocaris was different. It was part of the open water, or at least capable of moving through the water column in an active way. Its form suggests an animal that could search, approach, turn, and pursue. Not endlessly, not like a machine, but enough to make it one of the more mobile hunters of its world. The lateral flaps probably moved in coordinated waves. That means the body did not need to bend violently from side to side as a fish body often does. Instead, movement could pass along the flaps themselves, producing thrust while the body remained relatively stable. Stability matters when you're trying to aim your head at food. It is one thing to be fast. It is another thing to be fast while also keeping your eyes and feeding limbs properly lined up with the animal you intend to catch. Anyone who has tried to carry a full cup of tea while walking quickly knows that movement and control are not always close friends. This kind of swimming may have allowed Anomalocaris to cruise through the water with efficiency. If the flaps overlapped or worked together along each side, they could behave like a long, flexible fin. The result would not have been the stiff, darting movement of a modern fish, but a smoother, rippling propulsion. The animal may have been able to adjust the timing and movement of its flaps to rise, sink, turn, or maintain position. A body with many flaps gives many opportunities for control. It also gives many opportunities for things to go wrong, which is why it is fortunate that evolution had millions of years to sort out the basics and did not have to assemble Anomalocaris during a rushed afternoon meeting. At the rear of the body, a tail fan may have helped with steering. This is an important detail because catching prey is rarely just a matter of moving forward. A hunter must turn. It must correct its direction. It must respond when prey shifts course, sinks, rises, or escapes sideways. In water, turning can be difficult if your body is long and your speed carries you past the target. A tail fan can act like a control surface, helping the animal adjust direction. This would have been especially useful for a predator that relied on its front appendages. The head had to arrive in the right place. The feeding limbs had to reach at the right moment. Missing by a few centimeters might mean the difference between eating and simply looking dramatic. Picture it from the point of view of a smaller Cambrian swimmer. The water is not empty. Light filters down from the surface. Particles drift. Other animals move nearby. Then the shape appears. Large for its world. Long-bodied. Flaps moving along the sides. It is not shaped like the predators that will rule later seas. It has no jaw to gape open. It has no row of teeth in the modern sense. But it has eyes that can track motion, and it has those two front appendages. The predator does not need to roar, because roaring underwater would be a poor choice, and Anomalocaris was not a theatrical sea lion. It only needs to approach. The front appendages were central to its hunting style. They were segmented, curved, and equipped with spines. They projected from the head region, positioned where they could interact with prey before the mouth did. This is very different from a predator that simply bites with jaws. In Anomalocaris, the first contact may have been made by these limbs. They could reach, grip, sweep, or guide food toward the mouth followed behind as part of the feeding system. It was not a shark-like attack. It was more like a capture and handle process, with the appendages doing much of the important work. Recent research has suggested that the frontal appendages of Anomalocaris canadensis were suited for grabbing softer prey in open water, rather than crushing hard-shelled trilobites on the sea floor. This gives us a more focused image of the animal. It was not necessarily smashing armoured animals like a floating nutcracker. It may have been better understood as an active swimmer pursuing softer animals, using its speed, eyes, and appendages together. That picture is less like a tank and more like a hunter built for movement. Still dangerous, just in a more precise way. This matters because the Cambrian Ocean had many kinds of possible prey. Some animals were armoured, some were soft, some lived close to the bottom. Some swam or drifted in the water column. A predator does not need to eat everything to be successful. In fact, most predators do not. They have preferences and limits. Their bodies make some prey easier to catch, and some prey not worth the effort. If Anomalocaris was better at catching soft-bodied swimming animals, then its swimming flaps become even more important. It was not just moving around at random. Its whole body may have been part of an open water hunting strategy. The eyes supported that strategy. Large compound eyes would have given Anomalocaris a way to detect movement and track prey. Vision is especially useful for an active swimmer. A blind hunter can still succeed in some environments, especially if it uses smell, touch, vibration, or ambush. But a swimmer chasing moving prey benefits greatly from seeing where the prey is going. The eyes tell the body where to aim, the flaps provide movement, the tail fan adjusts direction, the appendages close the final distance, the mouth receives what the appendages bring in, the parts work together. When you think of Anomalocaris this way, the animal stops being just a strange shape and becomes a sequence of actions. It sees, it turns, it swims, it reaches, it feeds, The side flaps are not decorative. The tail fan is not an artistic flourish. The appendages are not strange ornaments hanging from the face. They are equipment. The Cambrian sea was not rewarding good looks, at least not by our standards. It was rewarding bodies that could solve problems. Anomalocaris solved the problem of active hunting in a world before Jaws had taken over the job. The phrase, hunter with swimming wings, also helps us avoid imagining it as clumsy. Some reconstructions of very ancient animals can make them seem awkward, as though early life was stumbling through its own design process and hoping no one noticed. But Anomalocaris was not a failed attempt at a fish. It was a successful animal within its own environment. Its swimming style may have been stable and effective. Its body was streamlined for the kind of movement it used. It did not need a fishtail because it was not a fish. Judging it for lacking one is rather like judging a bicycle for not having hooves. The water itself would have shaped how the flaps worked. Water is thick compared with air. It supports bodies, resists motion, and allows animals to push against it. Small changes in body shape can make a large difference. A broad flap can generate force. A flexible edge can reduce drag or create smoother movement. A series of flaps can work like a continuous surface if their motion is coordinated. Even without bones, an animal can be an effective swimmer if its soft tissues and body structure are arranged well. Modern cuttlefish, rays, and many marine invertebrates show that water can be mastered in more than one way. Anomalocaris likely swam with the head held forward and the appendages positioned in front. Some studies of its appendage posture suggest that holding them outstretched could reduce drag during rapid swimming in open water. That is a small detail with a big effect on how we imagine the animal. If the appendages were always hanging awkwardly or dragging through the water, they might slow the animal down. But if they could be positioned in a way that fit the flow of water, they could remain ready for use without ruining the animal's movement. It is the Cambrian version of carrying tools without tripping over them. This also adds to the idea of Anomalocaris as an active predator rather than a sluggish collector of scraps. A streamlined body, coordinated flaps, useful eyes, and appendages suited for capture point toward a creature that participated in the water column as a hunter. It may not have been constantly chasing prey at top speed. No animal lives like that unless it wants to become exhausted and unpopular with its own metabolism. Much of its life may have involved cruising, searching, adjusting position, and taking opportunities when they appeared. Predation is often patience interrupted by effort. The Cambrian sea would have offered many such opportunities. Small, soft-bodied animals swimming or drifting above the seafloor. Other arthropod-like creatures moving through the water. Worm-like animals exposed at the wrong moment. Anything soft enough to handle and slow enough to catch might have been a possible meal. The exact diet remains a subject of scientific interpretation, but the general role is clear enough. Anomalocaris was one of the animals making life more difficult for others. That difficulty is one of the engines of evolution. A predator with good swimming ability changes the risks around it. Prey cannot rely only on being somewhere nearby and hoping nothing happens. Movement becomes more dangerous. Open water becomes more dangerous. Visibility becomes more important. If Anomalocaris could see and pursue, then prey animals that reacted faster had an advantage. Animals with better defences had an advantage. Animals that hid, burrowed, or became harder to grasp had an advantage. In this way, the swimming flaps of one predator connect to the shells, spines, behaviours, and nervous systems of many other animals. It is easy to focus only on the chase, because chases are exciting, and because humans enjoy turning nature into tiny action films. But the larger story is ecological. Anomalocaris was part of a system. It did not simply rule by being large. It helped define what being prey meant in its environment. Its movement through the water was part of the pressure that shaped other lives. The swimming wings were not only a way to travel, they were a way to influence an entire community. Still, there is room for the simple image. Anomalocaris passing overhead, side flaps rippling, tail fan steadying the body, eyes scanning the water ahead, appendages slightly forward, ready but controlled. The animal is large enough to matter, but not so large that it belongs in the world of whales or giant reptiles. It is Cambrian large, which means impressive in context. A predator does not have to be huge by all future standards. It only has to be bigger, faster, or better equipped than many animals around it. The lack of a backbone did not make it primitive in the casual sense of weak or poorly made. Invertebrate animals can be strong, fast, complex, and highly successful. Arthropods today are among the most diverse animals on Earth, and they include hunters, swimmers, flyers, diggers, climbers, and animals that can find their way into sealed food containers with unsettling commitment. Anomalocaris belonged near the early history of that broader arthropod line. It shows that active, capable invertebrate predators were already important very early in complex animal ecosystems. Its flaps also remind us that evolution does not move toward one perfect answer. Fishtails work very well. Squid jet propulsion works very well. Ray-like undulation works very well. Jellyfish pulsing works well enough for jellyfish, who appear quite content with it. Anomalocaris used another method. The Cambrian Sea contained experiments in movement that did not all lead directly to modern forms. Some lasted for a time and disappeared. Others left descendants through related lines. The important point is that movement itself was becoming more varied and more capable. An animal that can swim well changes its options. It can search a larger area. It can escape unfavourable conditions. It can choose between parts of the water column. It can approach prey from different angles. It can avoid some bottom-dwelling hazards. It can cover distance without waiting for food to drift by. For Anomalocaris, swimming was not just transportation. It was access. Access to prey, space, and opportunity. The swimming wings open the sea. This is one reason the animal feels so different from earlier, more passive images of ancient life. It belongs to a time when animals were becoming more active participants in their environments. Not simply existing where currents placed them, but moving, sensing, and responding. The ocean was gaining behaviour, not human-like behaviour, of course. No plans, no maps, no meetings, no one saying, "Let us circle back on the trilobite situation." But behaviour in the biological sense, actions guided by bodies and nervous systems. The flaps of Anomalocaris were part of that shift. If we slow the scene down, we can imagine a single movement. The animal hangs in the water, body almost level, appendages angled forward. A small, soft-bodied creature moves ahead. The eyes detect it. The flaps begin a coordinated wave and the body advances. The tail fan adjusts the line of approach. The prey shifts. The predator turns. The front appendages extend or curl at the right moment, trying to trap the animal and bring it toward the oral cone. Maybe the attempt succeeds. Maybe it misses. Predators miss often. Nature is full of failed attempts, which is reassuring if you have ever tried to open a packet of biscuits quietly and failed completely. A successful hunt would have depended on timing. The appendages were not magical. They had reach, shape, and mechanical limits. The mouth had limits too. The prey might escape, slip away, or be too large, too armoured, or too close to the seafloor. The predator had to work within what its body allowed. This is why the swimming system matters so much. Good movement improves the chance of bringing the feeding limbs into the right place. A hunter with poor control wastes energy. A hunter with good control can make fewer movements count. The image of Anomalocaris as a graceful swimmer may feel surprising because its face is so strange. We tend to associate grace with familiar shapes. Birds, dolphins, manta rays and horses get called graceful. A Cambrian radiodont with a circular mouth and spiny head limbs has to work harder for the compliment. But in water, grace is not about looking gentle. It is about reducing waste. It is about a body moving in a way that suits the medium. Anomalocaris may have looked strange to us, but its movement could have been smooth, efficient and controlled. This makes it one of the most interesting predators in Earth's history. Not because it was the biggest predator ever. It was not. Not because it was the strongest. We cannot know that in any simple way. Not because it was the ancestor of every later hunter, because evolution is not that tidy. It matters because it shows us predation before the familiar toolkit, before jaws became famous, before fish dominated open water, before sharks became the standard symbol of marine danger. Here was a hunter using a different set of tools, and those tools worked. The idea of Anomalocaris ruling the first oceans should be understood in that context. It was not alone. It was not the only predator. It was not floating around the Cambrian Sea as the sole manager of unpleasant surprises. Other radiodonts and other animals fill different ecological roles. Some may have been bottom feeders, some may have sifted sediment, some may have captured different prey, but Anomalocaris, especially in the way it is often reconstructed from Burgess shale material, represents one of the clearest examples of a large active Cambrian hunter. It stands near the beginning of a long story of marine predation, and that story is not only about violence, it is about motion, perception, and adaptation. A predator must be able to find food. A prey animal must avoid becoming food. Between those two pressures, bodies change. Eyes become sharper, shells become tougher, limbs become better at grasping or escaping. Swimming improves, burrowing deepens, the seafloor changes, the water column becomes more active. Anomalocaris, with its swimming wings, belongs to this early acceleration of animal life. So let the creature move in your mind again, not as a flat fossil but as a body in water. Its flaps ripple from front to back. The motion travels along each side. The animal glides forward. It is not hurried in every moment. It does not need to be. A hunter spends much of its time looking for the right situation. The large eyes collect light. The front appendages wait in position. The tail fan gives balance and turning control. Around it, the Cambrian Sea is full of animals still new to the demands of complex ecosystems. Some crawl below, some swim nearby, some hide in sediment, some carry armour, some are soft, exposed, and worth pursuing. Nothing about this scene requires a modern fish. Nothing requires a shark. The ocean has already invented danger using older materials. It has built a predator with flaps instead of fins, appendages instead of jaws, and a mouth unlike anything most people expect. Anomalocaris is not a rough draft of later animals. It is its own answer to the problem of hunting in the early sea, and as it moves through the water, those swimming wings tell us something very simple and very important. The first oceans were not passive places. They were filled with animals learning how to move, how to sense, how to catch, and how to escape. Long before the sleek predators of modern seas, long before teeth became the symbol of underwater fear, a wide-eyed radiodont was already gliding through the Cambrian water, using waves of motion along its sides to turn the ancient ocean into a place where being seen could be dangerous. Anomalocaris becomes much easier to imagine when we stop looking at it as one strange outline and begin looking at the tools gathered at the front of its body. The eyes, the grasping appendages, and the circular mouth were not random features. They were the working equipment of a hunter in a sea where active predation was becoming one of the great pressures on animal life. If the side flaps were the engine, then the head was the control room, a very old control room admittedly, and one with a mouth that looks as if it was designed by someone staring too long at a sliced pineapple, but still a control room. Let us begin with the eyes, because eyes changed everything. Anomalocaris had large compound eyes, and that detail alone tells us a great deal about the kind of animal it was. A creature with well-developed eyes is not simply waiting for the world to bump into it. It can detect movement, it can judge direction, it can respond to shapes and shadows, it can treat the water around it as a space full of information. In a modern sea, that may sound ordinary, because so many animals use vision. Fish watch for predators, squid track prey, crabs wave their little eye stalks about like nervous periscopes. But in the Cambrian, good vision was a major advantage, and Anomalocaris seems to have had it in impressive form. Fossils from the Emu Bay Shale in South Australia have revealed large eyes attributed to Anomalocaris, around 2 to 3 centimetres across, with thousands of tiny lenses. These were compound eyes, like those seen in modern arthropods, although Anomalocaris itself belonged to an earlier branch near the arthropod line rather than being a modern crustacean or insect. A compound eye is not like a human eye with one large lens forming a single detailed image. It is made of many small units, each gathering light from a slightly different direction. The result can be excellent for detecting movement, tracking changes, and noticing things that shift across the visual field. For a swimmer in an ancient sea, that is extremely useful. It means the animal could search the water rather than simply sample it. A small Cambrian animal moving through the water may not have been thinking much about optics, which is probably for the best. But if a predator nearby had large compound eyes, that prey animal lived in a world where being visible mattered. Vision creates distance in predation. Touch requires closeness. Smell or chemical detection can work at range, but slowly and differently. Vision lets a hunter notice a target across open water and begin adjusting its movement before contact. That gives the predator more time to aim and gives the prey less time to make poor life choices, such as staying exactly where it is. The eyes of Anomalocaris also give the animal a surprisingly modern feeling, even though the rest of the body refuses to cooperate with anything modern. Eyes are familiar. We understand, without much explanation, that an animal with large eyes is paying attention to the world. Not paying attention in the human sense, of course. It was not reflecting on its goals or wondering if it had left the kettle on. But its nervous system was receiving light, processing signals, and turning that information into movement. That is enough. In evolution, a little useful information can become a very powerful thing. Now place those eyes at the front of a large swimming predator. Suddenly the body plan becomes less strange. The eyes find the prey, the swimming flaps move the body into position, the tail helps with steering, the front appendages reach or curl, the mouth receives what the appendages bring toward it. Each part supports the next. The creature may look like a collection of odd ideas to us, but it was not just a loose arrangement of Cambrian decorations. It was a coordinated animal. Those front appendages were among the most important parts of the entire body. They were long, segmented and curved, with spines projecting from them. Early fossil hunters did not immediately understand them because, when found alone, they looked like separate shrimp-like creatures. That is how Anomalocaris got its name, meaning something like unlike other shrimp or abnormal shrimp. It is a name born from confusion, which feels appropriate for a creature that spent decades being assembled piece by piece in the scientific imagination. One part was named as one animal. Another part was interpreted as something else. The body was understood gradually, like a puzzle, in which several pieces had first been filed in the wrong drawer. In life, the appendages were not separate shrimp and not decorative feelers. They were feeding tools. They sat at the front of the head and could interact with prey before the mouth did. This is a very different method from the jaw-based hunting we often imagine today. A shark bites with jaws. A crocodile snaps. A lionfish opens its mouth and creates suction. Anomalocaris had frontal appendages that could grasp, trap, or guide prey. They were, in a sense, the hands of the operation, though not hands in any human way. They were jointed capture limbs, built to bring food into reach. Each appendage was divided into segments, and those segments carried spines. The exact shape and spacing of these spines matter because they tell scientists what kind of prey the appendages could handle. A tool built to crush hard shells needs different mechanics from a tool built to catch soft prey. A nutcracker is not a butterfly net, and a butterfly net is not a nutcracker, unless something has gone badly wrong in the kitchen drawer. For a long time, Anomalocaris was imagined as a trilobite-crushing predator, using its appendages and mouth to attack armoured animals on the seafloor. It was an appealing image, partly because trilobites were common, partly because some trilobite fossils show injuries, and partly because Anomalocaris looks like the sort of creature people would blame for almost anything. More recent biomechanical work has made that old picture more cautious. Studies of Anomalocaris canadensis suggest that its frontal appendages were better suited for capturing soft-bodied prey and moving quickly through open water than for crushing heavily armoured trilobites. This does not make it less impressive. It makes it more specific. A predator that chases softer animals in the water is not a failed shell crusher. It is a successful hunter of a different kind. Nature does not hand out prizes for eating the hardest possible thing. It rewards animals that find a workable way to feed. The appendages probably operated by reaching forward and inward, helping trap prey against the front of the body, or guiding it toward the mouth. Their spines may have helped prevent soft prey from slipping away. If the prey was small enough and not too heavily protected, the limbs could hold it in position. The animal did not need to chew in the way we understand chewing. It needed to capture, handle, and get food through the oral opening. That sounds simple until one remembers that the prey had its own opinions on the matter, expressed mostly through movement. There is something almost mechanical about imagining those appendages in action. They curve ahead of the body, held ready as the animal swims. The eyes detect something, the body turns, the side flaps ripple. The appendages extend into the right position. The spines help form a trap. The prey is drawn closer. The mouth waits behind, not a bite in the familiar sense, more a sequence. See, approach, reach, hold, feed. It is a hunting style from before jaws became the sea's most famous invention. And then there is the mouth itself. The mouth of Anomalocaris is so distinctive that it almost steals attention from the rest of the animal. It is often described as an oral cone, made from plates arranged around a central opening. To modern eyes, it can look like a pineapple ring, a camera shutter, or the world's least welcoming flower. Earlier interpretations sometimes imagined it as a powerful circular crushing device, one that could clamp onto trilobites and crack them open. That image helped to make Anomalocaris famous as a Cambrian terror. But the real oral cone was not simply a ring of teeth in the modern sense. It was a set of plates forming a feeding opening, and its structure varied among radiodonts. In Anomalocaris canadensis, the oral cone was not a perfect simple jaw. It did not have an upper and lower half. It did not bite the way a vertebrate mouth bites. The plates were arranged around the opening, with some larger plates and smaller ones forming the ring. This kind of mouth belongs to a different feeding system. It may have helped grip or process food brought in by the frontal appendages, but it was not necessarily able to crush tough mineralized shells with ease. That is important because it changes the animal from a generic ancient monster into a real creature with limitations. Limitations make animals more believable. A monster can do whatever sounds dramatic. A real predator has to obey its own anatomy. The mouth can only open so far. The plates can only resist so much force. The appendages can only bend in certain directions. The body can only accelerate and turn within the limits of its swimming system. Anomalocaris was not a fantasy machine that ate everything in sight. It was an animal with tools suited to some tasks better than others. It may have been dangerous to soft-bodied prey and lightly protected animals, but less able to break into heavily armoured prey than people once assumed. This makes the mouth more interesting, not less. The pineapple ring shape was not there to frighten future museum visitors, though it has done a fine job. It was part of an integrated feeding system. Food captured by the frontal appendages would be brought toward that opening. The plates could help secure or manipulate the prey as it entered. The mouth did not need to look like a shark's jaws because the whole animal was using a different strategy. Sharks are later solutions. Anomalocaris was a Cambrian one. The position of the mouth also matters. In many reconstructions, it is placed on the underside of the head region, behind the frontal appendages. That means the appendages were not simply decorations in front of a mouth. They were the first stage of feeding. They reached out into the environment and brought food to where the mouth could use it. This arrangement is common in a broad sense among many animals. Feeding often involves tools near the mouth. Crabs have claws, insects have mouth parts, squid have arms and beaks, humans have hands, though humans also have the unfortunate habit of using those hands to eat crisps over a keyboard. Anomalocaris had frontal appendages, and in its world, that was enough. The eyes, appendages and mouth together show that Anomalocaris was built around the front of the body. Its head region was a cluster of action. Sight, capture and feeding were all concentrated there. This kind of front-end specialization is called cephalization in broader biology. The tendency for sensory organs and feeding structures to gather near the front of a moving animal. It makes sense. If you move forward, the front end meets the world first. It is useful to put the eyes, mouth, and handling tools where new information and new food are most likely to arrive. A predator with important equipment at the rear would spend much of its life making awkward U-turns. Anomalocaris was not alone in having specialized frontal appendages. Radiodonts as a group show a remarkable variety of these structures. Some had appendages suited for grasping. Others seem adapted for filtering or sifting. Some may have hunted large prey. Others may have fed on tiny particles. This tells us that radiodonts were not all the same kind of predator doing the same job. They occupied different ecological roles. Anomalocaris is famous because it is dramatic and relatively well known, but it belonged to a broader collection of animals experimenting with the possibilities of front appendages and unusual mouths. The phrase experimenting needs care, because evolution has no goal and no laboratory notebook. Still, from our view, radiodont diversity looks like a set of variations on a theme. Put appendages at the front, add spines, segments, or filtering structures. Pair them with a mouth and swimming flaps. Then let different lineages specialize. Some become active hunters, some gather smaller food, some feed near the bottom, some swim through the water column. The Cambrian did not produce one simple predator design. It produced a range of forms, and Anomalocaris was one particularly famous result. Its eyes probably helped it succeed as an active hunter. The Emu Bay shale eyes assigned to Anomalocaris have been interpreted as having very high lens numbers, suggesting strong visual ability for the time. This supports the idea that large radiodont predators were part of a Cambrian arms race, where prey animals evolved better defences and predators evolved better ways to detect and capture them. The word arms race can sound a little too modern, as if trilobites were meeting in committees to discuss security policy. But the basic idea is useful. When one animal evolves a better way to hunt, other animals may benefit from better ways to avoid being hunted. Over many generations, these pressures can shape whole communities. A well-seeing predator encourages a world where hiding matters. A grasping predator encourages a world where spines, shells, and slippery bodies matter. A predator with a circular mouth and capture limbs encourages prey to become harder to hold, harder to process, or harder to notice in the first place. The body of Anomalocaris is therefore not only about Anomalocaris, it is also about everything around it. Its eyes imply prey worth seeing. Its appendages imply prey worth grabbing. Its mouth implies food that needed to be moved from outside the body to inside it, which is one of life's oldest logistical problems. It is easy to imagine those features in a dramatic moment, but they also work during ordinary life. Most of the time, Anomalocaris may not have been lunging like a villain in a sea monster film. It may have cruised slowly, adjusted position, followed movement, and taken chances when they came. Predators are often quiet for long stretches. A cat spends far more time watching than pouncing. A crocodile spends far more time floating than snapping. A spider spends far more time waiting than rapping. Anomalocaris may have had its own ancient version of this rhythm, though with fewer sunbeams and no sofa. The eyes would have scanned. The appendages would have been held in a position that balanced readiness with swimming efficiency. The mouth would have remained part of the feeding system, not a constantly chomping machine. When prey appeared, the animal could act. This makes it feel less like a monster and more like an animal with routine. Hunt, feed, swim, rest, grow. Repeat, as long as the sea allows. The mouth's odd shape also shows how misleading modern comparisons can be. Calling it a pineapple ring is useful because it gives the listener an image. But a pineapple ring is not built to feed, unless one counts attracting hungry people at a buffet. The oral cone was a biological structure, made of plates and associated with muscles and tissues that are not preserved in the same way. What we see in fossils is only part of the living system. Soft tissues, movement, flexibility, and behaviour have to be inferred carefully. Fossils give us the framework, but the living animal was more than the hard pieces. The same is true of the appendages. In the rock they may look flat and still. In life they were three-dimensional structures attached to tissues moved by muscles and used in water. Their spines had direction and spacing. Their segments had flexibility. Their motion had limits. A fossil is a paused sentence. The living animal was the full paragraph, moving, reacting, and constantly being revised by circumstance. There is also something useful in remembering that Anomalocaris had no face in the emotional sense. Humans tend to read expression into everything. A dog's eyes look guilty. A cat's eyes look judgmental, often correctly. A car's headlights can look cheerful or angry. Anomalocaris tempts us to do the same, but its eyes, claws, and mouth were not expressions. They were functional structures. The animal was not menacing on purpose. It did not look strange to impress us. It had no opinion about being iconic. It was simply living inside a body that evolution had shaped for its environment. That body tells us that early animal life was already highly capable. The Cambrian Sea was not just a nursery of simple creatures, waiting for evolution to become interesting later. It already had complex sensory systems, active predators, specialized feeding tools, and ecological pressure. Anomalocaris stands out because its equipment is so visible and so unfamiliar. The eyes show perception, the appendages show interaction, the mouth shows feeding. Put them together, and we see one of the clearest early examples of a large predator built for the demands of an active ocean. From a distance, the creature looks like a dream with teeth. Up close, it becomes a set of practical solutions. The eyes helped it locate prey. The appendages helped it catch and handle prey. The oral cone helped it feed. The swimming flaps brought the body into range. The tail helped with control. Each part makes the others more useful. Good eyes are more valuable if the body can move toward what they detect. Grasping limbs are more valuable if the mouth can process what they bring in. A mouth is more valuable if food can be delivered to it. This is not chaos. It is coordination. That coordination is what made Anomalocaris one of the defining animals of its world. It was not just large, it was equipped. In an ocean full of soft bodies, small shells, new defences and new movement styles, it carried a suite of features that allowed it to hunt in a way very different from later marine predators. It did not need the jaws of a shark or the arms of a squid. It had its own Cambrian toolkit: wide eyes, spiny frontal appendages, a plated oral cone, swimming flaps, a body made for a sea where the rules of animal life were becoming more intense. As the animal moves through our imagined water, those parts come together. The eyes are not isolated fossils now, they are watching. The appendages are not mistaken shrimp now, they are reaching. The mouth is not a fossil jellyfish now, it is waiting at the centre of the feeding system. The whole creature becomes less like an old scientific puzzle, and more like a living presence in the Cambrian sea. And around it, the ocean is crowded with other animals, many of them just as unusual in their own ways, all taking part in a burst of biological variety that makes the Cambrian feel less like a quiet beginning, and more like a very busy world trying out more body plans than anyone could comfortably fit on a sensible diagram. The Cambrian Ocean was not a quiet test tank, where life politely tried one idea at a time. It was a crowded, changing, problem-filled place, and the animals living there were under pressure from every direction. Find food, avoid being eaten, move through water, hold onto the seafloor, stay hidden, grow a shell, lose the shell, burrow downward, swim upward, see danger, become danger. There was no manager, no plan, and no sensible checklist pinned to a piece of ancient seaweed, which is fortunate because there was not yet any seaweed of the familiar kind to pin it to. But from our distant point of view, the Cambrian can look like one of the busiest periods in the history of animal bodies. This is the time often called the Cambrian explosion. The phrase is dramatic, and it has stuck because it captures something real about the fossil record. Around this part of Earth history, many major animal groups become much easier to see in fossils. Bodies become more varied, hard parts become more common, movement becomes more active, predators and prey become more obvious. The seafloor gains trails, burrows, shells, spines, plates, limbs, eyes, mouths, and creatures that look as if they were assembled during a meeting where nobody wanted to be the first person to say, perhaps this is enough appendages. But the word explosion can also be a little misleading. It does not mean that one morning the ocean was empty, and by lunchtime it had trilobites, radiodonts, worms, sponges, early chordates, and a creature with 5 eyes and a long nose-like feeding tube. Evolution does not work like a surprise party. It works over generations, populations, environments, and time. The Cambrian diversification unfolded over millions of years. That is very fast by some geological standards, but still slow enough that no individual animal would have noticed it happening. A trilobite did not crawl along the seafloor thinking, goodness, biodiversity is really taking off this season. It simply lived, fed, grew, molted, reproduced if it could, and tried not to be handled by anything with spiny frontal appendages. Before the Cambrian, there were already animals and animal-like forms. Some Ediacaran organisms were large and soft-bodied, with shapes that are still difficult to interpret. Some looked quilted, some looked like fronds, some lay flat on the seafloor. Many of them do not fit comfortably into modern animal groups. Then, as the Cambrian record becomes clearer, we begin to see a different kind of world. Animals with more active bodies, animals with skeletons or shells, animals that burrowed, animals with clearer front and back ends, animals that could chase, defend and hide. The sea did not simply contain living things. It contained interactions that started to look more like the ecological relationships we understand today. One of the major changes was the rise of hard parts. Shells, spines, plates, and external skeletons became much more common. This was useful for the animals that had them, and also useful for us, because hard parts fossilize more readily than soft tissue. A shell is more likely to survive burial than a soft body, just as a ceramic mug is more likely to be found in an old cupboard than the biscuit that once sat beside it. This makes the Cambrian fossil record richer, but it also means we have to be cautious. We are not seeing every animal that lived, we are seeing what the rocks were able to preserve. Exceptional fossil sites are especially important here. Places like the Burgess Shale in Canada and the Chengjiang Biota in China preserve soft-bodied animals and delicate structures that would usually vanish. Without such sites, the Cambrian would look much poorer and simpler than it really was. We might know the shells and miss the soft animals. We might see the armour and not the strange bodies wearing none. We might think early animal life was mostly hard little fragments, when in reality the seas were full of soft, flexible, moving creatures that only rarely left good fossils behind. The Cambrian was not just a collection of shells, it was a living community. And what a community it was! There were trilobites, perhaps the most famous Cambrian animals after Anomalocaris itself. Trilobites had segmented bodies, jointed limbs, and hard exoskeletons. They crawled over the seafloor, molted as they grew, and came in many forms across their long history. Some were small, some grew larger, some had spines, some had eyes. They were not the helpless background extras of the Cambrian. They were successful animals in their own right, and they would remain important for hundreds of millions of years. But in the Cambrian seas they were also part of a world where predators were becoming harder to ignore. There were also sponges, which are among the most ancient animal lineages and are very good at making a living without seeming to rush. Sponges filter water, extracting food particles, and they do this with a level of patience that would make a meditation teacher feel underqualified. There were worm-like creatures that crawled, burrowed, or hunted in sediment. There were early arthropod relatives with jointed legs and armoured bodies. There were small shelly fossils, animals that left behind tiny mineralised pieces that can be difficult to connect to whole bodies. There were early chordates, small creatures near the line that would eventually lead to vertebrates. There were animals so odd that even their names sound like someone tried to describe them after a very confusing dream. Opperbinia is one of the classic examples. It had 5 eyes and a long flexible proboscis ending in a grasping structure. This is not a creature designed to comfort anyone who prefers animals with a familiar number of facial features. When early reconstructions of Opperbinia were presented, the story goes that the audience laughed. Not because the science was poor, but because the animal looked so unexpected. Hallucigenia is another famous Cambrian form, a small animal with spines and legs that was once reconstructed upside down. That may sound embarrassing, but really it is understandable. When an animal looks like hallucigenia, deciding which side is the top is not as straightforward as one might hope. Even nature seems to have looked at it and said, let them work for it. The Cambrian Ocean was filled with animals like this, not because evolution had lost control, but because many lineages were exploring different solutions to the same basic problems. How do you move? How do you eat? How do you avoid being eaten? How do you protect soft tissue? How do you sense the world? How do you reproduce successfully in a sea full of other hungry organisms doing their own best efforts? Some solutions became common in later history. Others disappeared. Some body plans left descendants. Others became extinct branches. Looking back, the Cambrian can feel like a crowded workshop of animal design, though there was no designer and no blueprint. Only variation, survival, extinction, and time. Eyes were one of the most important developments in this world. Once animals could see well, the sea changed. A predator with vision can detect prey at a distance. A prey animal with vision can detect danger before contact. This turns the environment into a more active space. Movement matters more. Shadows matter. Distance matters. Direction matters. A world without good vision is still full of information, but much of that information comes through touch, chemistry, vibration, and light sensitivity. A world with eyes becomes more immediate. Something can spot you before it touches you. That is a serious change in the rules. Anomalocaris fits neatly into this story because it had large eyes and was likely an active swimmer. It was not just a big shape drifting around. Its eyes, flaps, appendages, and mouth all suggest an animal built to engage with the world around it. It could move through the water, it could locate prey, it could reach with its frontal appendages, it could feed using its unusual oral cone. In a Cambrian sea full of small and soft animals, that combination made it one of the most impressive predators of its time. Predators create pressure. That is one of the key points of the Cambrian Ocean. When predators become more active or more effective, prey animals benefit from defences. Shells and spines become useful. Burrowing becomes useful. Faster movement becomes useful. Better vision becomes useful. Hiding becomes useful. Even being unpleasant to eat becomes useful, which is a strategy that certain modern animals and a few badly cooked vegetables have continued with determination. Over long periods, these interactions can produce an evolutionary arms race, where improvements in hunting are matched by improvements in defence, and then those defences encourage new hunting strategies. This does not happen because animals are planning against each other. A trilobite does not decide to evolve better armour after seeing a radiodont and thinking, I must improve my personal safety policy. Instead, individuals with traits that help them survive tend to leave more descendants. If a slightly tougher shell improves survival, that trait can become more common. If better vision helps a predator catch food, that trait can spread in predator populations. Evolution is not a conscious contest, but it can produce results that look like one from a distance. The Cambrian also saw changes in how animals used the seafloor. Burrowing became more common and more complex. This is a bigger deal than it might sound. A seafloor covered mostly by microbial mats is very different from a seafloor stirred and tunneled by animals. Burrowers mix sediment, create hiding places, change oxygen flow, and alter the habitat for other organisms. Once animals begin digging into the bottom, the seafloor stops being only a surface and becomes a three-dimensional living space. There is life above it, on it, and within it. That is a major ecological shift, even if it looks, at first glance, like a lot of small creatures making messy tunnels. These changes affected predators too. If prey could burrow, predators had to search differently. If prey had shells, predators needed ways to handle or avoid them. If prey became faster, predators needed better movement or better timing. Every change in one part of the community affected other parts. The Cambrian Ocean was not a simple list of animals. It was a network of relationships, and those relationships helped shape the future of animal life. Oxygen may have played an important role as well. More active bodies need energy. Larger bodies need energy. Predation, swimming, burrowing, and building hard parts all place demands on an organism. Higher oxygen levels in the environment may have helped support more active lifestyles, although the full explanation for the Cambrian diversification is not simple. Scientists have discussed many interacting factors, including oxygen, genetics, ecology, predation, environmental change, and the evolution of developmental systems that allowed more complex bodies. It is tempting to choose one cause and call the case solved, because one cause is tidy and easy to remember. But the real Cambrian was not tidy. It was a mixture of conditions and opportunities, and life responded in many ways at once. Genetic changes also matter, though they are harder to see directly in fossils. Animals build bodies using developmental instructions inherited from their ancestors. Changes in these systems can alter body plans, segments, limbs, shells, and organs. By the Cambrian, animals had the biological toolkit needed to produce a wide range of forms. The fossil record shows the results: bodies with repeated parts, specialized heads, limbs, eyes, armor, spines, and feeding structures. The animals themselves did not know they were carrying developmental toolkits. They were simply growing according to inherited processes. But those processes made complex bodies possible. The result was a sea full of variety. Some animals were flat, some were long, some were armoured, some were soft, some swam, some crawled, some burrowed, some filtered food, some hunted, some likely scavenged. Some probably did several of these things when the opportunity arose, because nature is not always strict about job descriptions. A creature can graze most of the time and still take advantage of a dead animal nearby. A predator can scavenge. A filter feeder can live in a dangerous neighbourhood. Ecosystems are practical, not tidy. Anomalocaris lived within this variety. It was not floating through an empty stage. Around it were animals with different sizes, shapes and defences. Some would have been too armoured to handle easily. Some too small to be worth chasing. Some too hidden in sediment. Some soft and exposed. A successful predator does not need to eat every possible animal. It only needs enough suitable prey to make its lifestyle work. Anomalocaris likely hunted in a sea where many organisms were newly vulnerable to active swimmers with good vision. The Cambrian Ocean also reminds us that extinction is not failure in any moral sense. Many of these strange forms eventually vanished. Their lineages ended or changed beyond recognition. But while they lived, they were not failed attempts. They were functioning animals in functioning ecosystems. Opabinia was not a mistake. Hallucigenia was not a joke. Anomalocaris was not an evolutionary rough draft waiting for sharks to arrive and do the job properly. These animals belonged to their own time. They were the successful living things of their own seas, even if they later became fossils that make modern people squint at diagrams. This is an important correction to how we often think about evolution. Evolution is not a ladder leading from strange to sensible, from primitive to perfect, from Anomalocaris to us, with every step applauding politely as the next one arrives. It is a branching process. Many branches grow, some continue, some end, some split. Some produce familiar animals, some produce forms that disappear completely. We are not the goal of the Cambrian. Sharks were not the goal of the Cambrian. The Cambrian animals were not waiting for the future to judge them. They were living in the present of their own world. And that present was full of invention in the ordinary biological sense. Trilobites with hard exoskeletons, worms with teeth or spines, early arthropods with jointed limbs, radiodonts with frontal appendages and swimming flaps, sponges filtering water, small animals making shells, others digging into sediment, some using eyes, some using armour, some using speed. Each body was a response to a life problem. None was perfect. All were temporary. That is true of every body, including ours, though ours has the added design issue of occasionally hurting its back while sleeping in a slightly unusual position. The phrase, where evolution got carried away, is useful because the Cambrian feels crowded with novelty. But the truth is that evolution was not carried away in the emotional sense. It was not excited, reckless, or over-caffeinated. It was simply producing variation in a world where many ecological roles were opening or changing. Some animals could now move more actively, some could build hard parts, some could see, some could hunt, some could hide. These possibilities allowed many lineages to diversify. From the outside it looks wild. From inside the process, it is only life responding to conditions. Still, the wildness is real in its effect on us. When we look at Cambrian fossils, we see forms that resist easy naming. We are used to sorting animals quickly. Fish, crab, worm, snail, jellyfish, insect, spider. Cambrian animals often interrupt that habit. An animal may look partly like an arthropod, partly like nothing alive, partly like a diagram that lost a bet. That difficulty is valuable. It reminds us that our categories are built from living species and better-known fossils. Deep time contains more possibilities than the present shows us. This is why Anomalocaris stands out so well in the Cambrian. It is strange, but it is strange in a world where strangeness is common. It is large, but not alone in being unusual. It is predatory, but part of a wider shift toward more complex ecological interactions. Its eyes belong to a world where vision mattered. Its appendages belong to a world where prey could be caught and handled. Its flaps belong to a world where active swimming had become useful. Its mouth belongs to a world before jaws became the standard equipment for large marine hunters. The Cambrian Ocean was also not brightly modern in the way many illustrations might suggest. We do not know the exact colours of most of these animals. Fossils usually preserve shape better than colour, especially across such vast time. Some animals may have been dull, some may have had patterns, some may have been translucent, some may have blended with sediment. The water itself would have carried particles. The light would have changed with depth and location. It is easy to imagine the Cambrian as a clear aquarium full of perfectly visible creatures, but real oceans are messier. Visibility changes, sediment moves, bodies hide, predators search in imperfect conditions. This makes vision even more interesting. Large eyes do not guarantee a perfect view. They give an animal more information than it would otherwise have. In water with shifting light and suspended particles, detecting motion may be more important than seeing fine detail. A prey animal's movement, a shadow, a change in contrast, or a shape against the background could be enough to guide a predator. Anomalocaris did not need to see like a human reading a sign. It needed to see well enough to hunt. The prey animals, in turn, did not need to understand Anomalocaris. They needed to survive encounters. Some may have done so by being armoured, some by hiding, some by living in sediment, some by being small or hard to detect, some by reproducing in large numbers, which is a common and rather blunt solution to the problem of danger. If many offspring are produced, some may survive even when predators are common. It is not a sentimental strategy, but nature rarely consults sentiment before setting policy. In this ocean, life was becoming more layered. The surface waters, the open water, the seafloor and the sediment each offered different ways to live. Animals could specialise in one zone or move between them. Predators could search above the bottom or along it. Burrowers could escape downward. Swimmers could escape sideways or upward. Filter feeders could stay attached. Crawlers could follow food across the sediment. This layering made the ecosystem more complex. It gave life more places to be and more ways to interact. Anomalocaris, with its swimming body, belonged especially to the active part of this system. It could move across space in ways many bottom-dwelling animals could not. That gave it access to prey, and perhaps allowed it to cover larger areas. Its presence would have made the water column a more dangerous place for suitable animals. It may also have connected different parts of the ecosystem by feeding on one kind of animal and affecting the behaviour of others. Large predators often have effects beyond the animals they actually eat. Their mere presence can change where prey go, when they move, and how they behave. That is a very old pattern. In modern ecosystems, predators shape prey behaviour all the time. Fish form schools. Antelope gather in groups. Small mammals avoid open spaces. Birds freeze when a hawk passes overhead. In the Cambrian, the details were different, but the broad pressure was already present. If a large swimming predator could spot and capture prey, then prey animals lived under a new kind of risk. The ocean was not just a place to feed, it was a place to watch, hide, and react. So the Cambrian was not strange only because the animals looked strange. It was strange because the rules of animal life were becoming more intense, bodies were becoming more interactive, the seafloor was being disturbed, hard parts were spreading, eyes were changing behaviour, predators were shaping defences, movement was opening new habitats. Soft-bodied animals, armoured animals, swimmers, crawlers, burrowers and filter feeders all shared a sea that was becoming more complex by the generation. And somewhere in that sea, Anomalocaris moved with its side flaps, using a body plan that belonged entirely to that early world. It was not waiting to become something else. It was not a preview of sharks. It was one of the animals that made the Cambrian Ocean feel, to us, like evolution had thrown open a drawer of possibilities and forgotten to close it again. Around it, other creatures crawled, drifted, dug, watched, and fed. Some carried armour, some carried spines, some carried eyes. Some carried no obvious defence at all, which may have been unfortunate depending on the direction from which Anomalocaris approached. The more we look at this ocean, the less it seems like a simple beginning. It was already a world of strategies. Not human strategies, not conscious plans, but body strategies. The shell strategy. The swimming strategy. The burrowing strategy. The seeing strategy. The grasping strategy. The filtering strategy. The hiding under the sediment and hoping for the best strategy, which remains understandable in many areas of life. Each animal carried its strategy in its body. That is the setting that gives Anomalocaris its meaning. Remove the Cambrian variety, and it becomes only a strange predator. Place it back among trilobites, worms, sponges, early arthropods, soft-bodied animals, burrowers and swimmers, and it becomes part of a much larger change. It is one answer among many in a sea where evolution was producing more shapes, more interactions, and more ways to survive than Earth had seen before. The first oceans of complex animal life were not gentle classrooms. They were living systems with consequences. A shell could save you, a shadow could warn you, a better eye could guide you, a faster turn could feed you, a deeper burrow could hide you. A pair of spiny frontal appendages could end the day for something soft and unlucky. This was the Cambrian Ocean, not familiar, not simple, and not as peaceful as its age might make it seem. It was old, yes, but it was not sleepy. It was active, crowded, and full of bodies trying out ways to live in a world where the next major change might be swimming just ahead, with wide eyes, side flaps, and a mouth shaped like a warning. Anomalocaris did not need bones to be powerful. It did not need jaws to be dangerous. It did not need teeth in the way we normally understand teeth, or a backbone, or a skull, or the sleek body of a shark. It came from an older world, a world before the sea had chosen many of its later symbols of strength. And yet in that Cambrian ocean, among animals that were often small, soft, slow, or only beginning to experiment with armour, Anomalocaris had enough. That is one of the most interesting things about it. When we think of a ruling predator, the mind tends to reach for large bones, heavy muscles, snapping jaws and rows of teeth, a Tyrannosaurus skull in a museum, a crocodile closing its mouth with unpleasant certainty, a great white shark cruising through blue water with the expressionless confidence of something that has never once worried about a parking ticket. These are the images we inherit from later life. But Anomalocaris ruled, if we use that word carefully, with a very different set of tools. It had no skeleton of bone. It had no vertebral column. It had no jaw joint. It had no true teeth like a mammal, reptile, or shark. What it had instead was a flexible swimming body, large eyes, spiny frontal appendages, and a circular mouth made of plates. That was enough to place it near the top of its world. To understand why, we have to shrink our expectations down to Cambrian scale. A predator does not need to be enormous in every possible age. It only needs to be large and capable compared with the animals around it. In a modern ocean, an animal half a metre long is not automatically terrifying. It might be a respectable fish, a curious seal pup, or something you would point out while snorkeling and then immediately forget because a turtle went by. But in many Cambrian communities where much of the animal life was far smaller, a creature the length of a large cat, moving through the water with eyes and grasping appendages would have been a major presence. Size is always a local fact. A mouse does not care that a cat is smaller than an elephant. The mouse has more immediate concerns. In the same way, Cambrian prey did not need an Anomalocaris to be whale-sized for it to matter. They only needed it to be big enough, fast enough, and well-equipped enough to catch them. And it was well-equipped, though not in the way earlier scientists sometimes imagined. For many years, Anomalocaris was pictured as a terrifying trilobite crusher. It seemed to fit. There were trilobites with hard exoskeletons. There were fossil injuries on some of them. There was this large predator with spiny appendages and a round mouth. the story practically wrote itself. Anomalocaris swoops down, grabs trilobite, cracks shell, eats the soft parts, and swims away, looking like the Cambrian's least approachable dinner guest. But paleontology, like a careful friend, often steps in just when the story has become too neat. More recent biomechanical studies suggest that Anomalocaris canadensis was probably not especially good at crushing hard trilobite shells. Its frontal appendages may have been damaged by the forces needed to grab tough armoured prey, and its mouth may not have been suited to powerful shell cracking. Instead, it seems more likely that it was agile, fast, and better adapted to catching softer prey in open water. This does not make it less of a predator. It makes it a more realistic one. A predator does not need to crush armour to rule a space. A falcon does not bite through tortoise shells. A squid does not need to eat steel cans. A jellyfish does not need a jaw at all, and still many small animals would prefer not to bump into one. Every hunter has limits. The successful ones find prey that match their tools. Anomalocaris may not have been the Cambrian's armoured shell destroyer, but it could still have been one of its great open water hunters. Less like a tank, more like a fast-moving capture machine with face appendages, which is not a phrase anyone needs to hear at breakfast. Its lack of bones was not a weakness in the way we might assume. Bones are useful, certainly. They support large bodies, anchor muscles, protect organs, and allow vertebrates to do many impressive things, such as running, flying, swimming, and sitting badly in chairs. But bones are not the only way to build an effective animal. Arthropods use exoskeletons. Squid and octopuses use mostly soft bodies with specialised internal supports. Worms, jellyfish, and many other animals use fluid pressure, flexible tissues, shells, plates, or entirely different body plans. Life has never been limited to one engineering style. Anomalocaris belonged near the early history of arthropods, in a group called radiodonts. These animals had bodies that were not built around internal bones, but they could still move actively and develop complex structures. Their side flaps powered swimming. Their frontal appendages handled food. Their eyes provided information. Their oral cones processed what came close enough to eat. They show us that long before backbones became central to many large predators, invertebrate animals were already taking on powerful ecological roles. It is useful to remember that the Cambrian Sea did not yet have the familiar vertebrate predators that dominate many later marine stories. No sharks, no tuna, no marine reptiles, no seals. No dolphins, no swordfish doing anything dramatic. In that world, a large active invertebrate swimmer could occupy a role that later belonged to jawed fish and other vertebrates. The seat was open, so to speak, and Anomalocaris did not need a skeleton to sit in it, though sitting would have been difficult with all those flaps. Its power came partly from mobility. Many Cambrian animals lived on or near the seafloor. Some crawled, some burrowed, some filtered food, some drifted or swam weakly. Anomalocaris, by contrast, had a body designed for movement through the water column. Its lateral flaps could ripple in coordinated waves, pushing it forward and giving it control. A tail fan may have helped it turn quickly. This made it more than a passive feeder. It could search, it could reposition, it could approach prey from different angles. It could move through an environment rather than simply wait for food to arrive. Movement changes power. A stationary predator can still be dangerous, of course. A sea anemone does not chase you, but small animals drifting into it may still have a difficult afternoon. But an active predator expands its reach. It can choose where to go. It can follow prey. It can patrol. It can leave one patch of water and enter another. It can make the environment feel larger for itself and smaller for its prey. Anomalocaris, with its swimming flaps, would have been able to turn the Cambrian Sea into hunting space. Then there were the eyes. Large compound eyes gave it another advantage. A predator that can see well can detect prey before contact. It can respond to movement at a distance. It can adjust its course. Vision gives the water shape. It turns shadows, motions, and contrasts into information. For an active swimmer, that is valuable. Swimming without vision can work, but swimming with vision changes what is possible. The animal can pursue rather than merely encounter. It can aim rather than simply hope. This is where Anomalocaris begins to feel like a true ruler of its environment, not because it was cruel, and not because it possessed some dramatic hunger beyond other animals. The phrase, "without mercy," is a human phrase, and we should handle it gently. Anomalocaris did not have mercy in the moral sense because it did not have morality. It did not choose to be ruthless. It was not patrolling the Cambrian sea with a tiny ancient grudge. It was a predator, and predators feed. To the animals it caught, that distinction would not have been very comforting, but it matters to us. Nature is not merciful or merciless in the way people are. It simply operates through bodies, needs, opportunities, and consequences. Anomalocaris ruled without mercy because the Cambrian sea did not run on mercy. It ran on survival. If a soft-bodied animal was visible, reachable, and slow enough, then the predator's appendages could close the distance. If a prey animal escaped, it lived a little longer. If it did not, its body became energy for another body. There is no villain in that exchange. There is only life doing what life has done from its earliest animal histories onward. Those frontal appendages were the direct tools of that survival. They were jointed, curved, and lined with spines. They likely helped capture prey and bring it toward the mouth. Without jaws, Anomalocaris needed another way to handle food. The appendages did what jaws alone could not do. They reached beyond the mouth. They contacted the prey first. They formed the beginning of the feeding process. In a modern predator, the mouth often dominates the image. In Anomalocaris, the appendages deserve just as much attention. They were not accessories. They were the hunter's main grabbing equipment. Imagine a small, soft animal swimming or drifting in the Cambrian water. It may detect light, vibration, or chemical signals. It may respond to shadows. But if Anomalocaris is approaching from the right direction, the predator has eyes, movement, and reach. The flaps carry it closer. The tail helps correct the approach. The appendages extend into range. Their spines help trap or hold. The prey is guided toward the circular mouth. It is not the clean snap of jaws. It is a more ancient sequence of capture. The mouth itself was unusual enough to become one of the creature's most famous features. The oral cone, made of hard plates arranged around a central opening, looks to us like a ring of teeth, though it was not teeth in the vertebrate sense. In older depictions, it sometimes appears as a crushing wheel of doom, which is a wonderful phrase but not necessarily good anatomy. More careful studies have shown that Anomalocaris mouthparts were different from the classic Patoia-style oral cone, and may not have been capable of strong biting motions against hard prey. Again, we come back to the same idea. It was not weak, it was specialized. Specialization is not failure. A spoon is poor at cutting bread, but that does not make it a bad spoon. A pair of tweezers is poor at rowing a boat. A butterfly net will not open a walnut. Tools make sense only in relation to their task. Anomalocaris had tools suited to catching and eating certain kinds of prey. In the Cambrian water, that was enough to make it one of the most important predators. Its dominance also depended on what other animals lacked. Many prey species were still early in the long evolutionary history of defense. Some had armor. Trilobites, for instance, had hard exoskeletons and could enroll in some later forms, though not all early trilobites had the same abilities. Other animals had spines, some burrowed, some hid. But the full range of later marine defences had not yet developed. There were no fast fish schools flashing away in coordinated turns, no large hard-shelled crabs with heavy claws. No modern reef systems packed with hiding places shaped by hundreds of millions of years of evolution. The Cambrian had defences, but it also had many opportunities. Anomalocaris existed at a time when being a large active swimmer with good vision could make a dramatic difference. It did not have to be perfect. It did not have to win every chase. It did not have to eat every armoured animal. It only needed enough success to occupy a high place in the food web. Predators miss. Predators fail. Predators waste energy. A hawk does not catch every bird. A cat does not catch every mouse, despite what the cat may later imply. Success in nature is not perfection. It is enough survival and reproduction over time. This is important because the word apex predator can create a misleading image. We imagine a creature invincible in its environment, feared by all, challenged by none, perhaps accompanied by an orchestra. Real apex predators still get injured. They still starve. They still avoid risky prey. They still choose easier meals when available. They are top predators because few or no animals regularly prey on healthy adults, and because they occupy a high trophic role, not because they are unstoppable. Anomalocaris likely had vulnerabilities. Its appendages could be damaged. Its soft body could be injured. It had to find enough prey. It had to compete with other animals. It had to survive changes in its environment. Still, within its world, it was formidable. It had a combination of features that many animals around it did not. Size, mobility, vision, capture limbs, a feeding mouth. These things work together to create ecological power. A small animal with a shell might resist some attacks. A soft swimmer might escape some chases. A burrower might avoid exposure. But a predator like Anomalocaris forced many of those strategies to matter. It helped make the sea a place where animals could not simply exist, without being part of a larger web of threat and response. In this sense, Anomalocaris ruled not by force alone, but by pressure. Its presence may have shaped prey behaviour and evolution. Animals that were harder to see, harder to catch, harder to handle, or better defended would have had an advantage in a world with active predators. Over many generations, those advantages matter. Predation does not just remove individuals, it changes which traits become useful. This is one of the quiet powers of a predator. Even when it is not eating, it can influence the bodies and behaviours of other animals. Modern ecosystems show this clearly. When predators are present, prey often move differently, feed differently, and use habitats differently. They may avoid open spaces, form groups, come out at different times, or spend more energy watching for danger. The Cambrian evidence is more distant, of course, and we cannot watch Anomalocaris interact with living prey, but the rise of active predators, the appearance of defensive structures, and the increasing complexity of animal movement all suggest a sea where predator-prey relationships were becoming increasingly important. Anomalocaris also ruled by being part of a new kind of animal life. It was not just eating, it was participating in the transformation of ecosystems from relatively simple arrangements into more dynamic ones. Before active predators became common, many animals could live in ways that were less shaped by pursuit. Once predators like Anomalocaris entered the water column, the rules changed. Seeing mattered, speed mattered, armour mattered, burrows mattered. The sea floor and water above it became more dangerous and more complex. All of this happened without bones and jaws. That is the point worth resting on. We sometimes treat vertebrate features as the standard of animal success because we are vertebrates, and humans are famously fond of mistaking themselves for the measuring stick of everything. But the history of life is full of successful bodies built on different principles. Anomalocaris shows that a soft-bodied, flap-swimming, appendage-grasping animal could become a major predator in one of Earth's earliest complex marine ecosystems. It did not need to resemble us, or a shark, or any later hunter. It only needed to fit its own time. Its lack of jaws may even have made it more interesting. Jaws are so effective that once they became widespread among vertebrates, they changed marine predation enormously. But before that, animals had other options. Appendages could grasp. Mouthparts could suck, grip or process. Spines could trap. Flexible bodies could maneuver. The Cambrian sea was not waiting around for Jaws to make predation official. Predation was already happening, using whatever structures evolution had available. This gives Anomalocaris an almost transitional feeling, though it is not simply a bridge to something else. It represents a world before the familiar predator toolkit, a world where the top hunter could look radically different from the animals that later filled similar roles. In that sense, it is not primitive, it is early. There is a difference. Primitive is often used carelessly to mean crude or inferior. Early simply means belonging to an earlier branch of the story. Anomalocaris was not crude. It was well suited to a Cambrian problem. It was a working animal in a working ecosystem. If you place it in a modern ocean, it seems strange and perhaps vulnerable. It would share water with fish that move faster, cephalopods with advanced nervous systems, crustaceans with powerful claws, and predators with jaws, teeth, and refined hunting strategies. But place it back where it belongs, in the Cambrian, and it becomes impressive again. Context restores the animal. It was not designed for our seas, it was shaped by its own. The phrase, ruled without mercy, also hints at the way natural selection operates. There is no kindness in the matching of body to environment, but there is also no malice. A poorly protected animal caught by Anomalocaris did not fail morally. It simply met a predator whose body was better suited to that moment. A predator that missed did not fail morally either. It spent energy and remained hungry. The Cambrian sea was not fair, but fairness is not a biological law. Survival is local, temporary, and often very specific. This can feel harsh, but it is also the engine behind the variety we have been exploring. Without danger, there is less pressure for defense. Without defenses, there is less pressure for new hunting strategies. Without competition, there is less pressure to specialize. The beauty and strangeness of life are tied to these pressures. Shells, eyes, speed, camouflage, burrows, spines, schooling, warning colours, claws and careful behaviour all come from a world where survival is not guaranteed. Anomalocaris was part of that old pressure. Its hunger helped right the bodies of others, and yet it was not only a force acting on prey, it was also acted upon. Its own body was shaped by the prey it pursued, the water it moved through, the competitors it encountered, and the limits of its anatomy. The appendages became useful because they could capture certain prey. The eyes became useful because prey could be detected visually. The flaps became useful because moving through water opened opportunities. The mouth became useful because it processed the prey the appendages delivered. A predator is not outside the ecosystem. It is held inside it, shaped by it, as much as it shapes others. That makes Anomalocaris less like a ruler on a throne and more like a powerful current in a living sea. It influenced the world around it, but it was also bound by that world. It could not eat everything. It could not survive everywhere. It could not stop evolution from moving on. For a time, though, animals like it occupied a major place in marine ecosystems. They were among the first large active predators, and their presence tells us that the Cambrian Ocean was already a place of pursuit, defence, and consequence. So when we picture Anomalocaris ruling, we should not imagine a monster roaring across the sea. We should imagine movement, the quiet ripple of lateral flaps, the slow adjustment of a tail fan, the steady attention of compound eyes, the front appendages held ready, their spines forming a trap, the circular mouth waiting behind them. Around it, smaller animals move through water and sediment, some armoured, some soft, some hidden, some exposed. The predator does not hate them, it does not pity them, it simply lives. That may be the most ancient kind of rule there is. Not command, not cruelty, not a crown, just the ability to make other animals evolve around your presence, to make shells matter more, to make hiding matter more, to make movement matter more, to turn open water into a risky place. Anomalocaris did this without bones, without jaws, and without anything we would recognise as mercy. It ruled because, in that early sea, its body was enough. And the more closely we look at that body, the clearer the old ocean becomes. It was not a peaceful prelude to later life. It was already full of pressure and adaptation. Anomalocaris was one of the animals that made the Cambrian Sea sharper. Not modern, not familiar, but sharp. And below it, around it, and sometimes inside its grasp, other creatures were finding their own answers, building armour, digging deeper, moving faster, and becoming part of an ancient contest that would continue long after Anomalocaris itself had vanished from the water. The fossil story of Anomalocaris begins with a problem that sounds simple, but is not simple at all. What happens when an animal is so strange that, after it dies, its body falls apart into pieces that look like several different animals? A claw becomes a shrimp, a mouth becomes a jellyfish, a body becomes something else. A predator is broken into clues, and each clue is filed away under the wrong name, waiting for someone in the future to notice that the ocean has played a very old trick. This is not because the early scientists were foolish. That is important to say. They were working with flattened fossils from animals unlike anything alive today, preserved in dark shale, often incomplete, often separated, and often showing only certain parts clearly. Paleontology is not like finding a complete toy in a box with instructions. It is more like finding a wheel in one field, a handle in another, a bell in a museum drawer, and eventually realizing that all of them belong to a bicycle that no one has ever seen before. And then, just to be difficult, the bicycle turns out to have face claws. The first major piece of the Anomalocaris puzzle was described in the late 19th century. In 1892, Joseph Frederick Whiteaves described fossils that he interpreted as the bodies of shrimp-like crustaceans. They were long, segmented, curved structures with spiny projections, and they did look, in isolation, like something that might belong to a small arthropod. He named the fossil Anomalocaris canadensis, with the name meaning something like unlike other shrimp, or strange shrimp. That name survived, but the interpretation did not. Those so-called shrimp bodies were not bodies at all. They were the frontal appendages of a much larger animal. Whiteaves had not named the whole creature. He had named its grabbing tools. There is something wonderfully awkward about that. Imagine discovering a fossil hand and, instead of realizing it is part of a larger animal, naming it as a complete creature. To be fair, if the hand belonged to an animal no one had ever imagined, you might do the same. A single Anomalocaris appendage does not immediately announce itself as part of a huge Cambrian predator. It looks like a curved, segmented thing with spines. In a world where many Cambrian fossils already seem to be testing the patience of classification, a mistake like that is not surprising. It is almost expected. Then came another piece of the animal, and this one caused its own confusion. Charles Doolittle Walcott, the famous collector and describer of Burgess Shale fossils, found a circular fossil that he interpreted as a jellyfish. He named it Peitoia nathorsti in 1911. Seen alone, the fossil made a kind of sense as a flattened disc. It looked like a round, soft-bodied creature preserved in stone. What it did not obviously look like was the mouth of a large predator. A mouth, after all, is usually expected to be attached to a face, and this one had arrived alone, like a very rude dinner plate. So there, in separate scientific boxes, were two parts of the same broad mystery. The strange shrimp was not a shrimp. The jellyfish was not a jellyfish. One was a grasping appendage, the other was a mouth. But no one yet had the complete animal clearly enough to bring them together. The Cambrian Sea had been divided into pieces by death, burial, geology, and human interpretation. The predator was hidden in plain sight, but only as fragments. This is one of the reasons the Burgess Shale is so important and so humbling. It preserves soft-bodied Cambrian animals in exceptional detail, but even exceptional detail does not always make interpretation easy. A fossil can be beautifully preserved and still misunderstood. It can show a structure clearly while hiding what that structure meant in life. If a body part is detached, flattened or preserved at an odd angle, the fossil may be honest and confusing at the same time. The rock is not lying. It simply does not explain itself. For decades, Anomalocaris remained scattered across scientific understanding. Different parts were assigned to different animals. The frontal appendages had their own identity. The oral cone had another. A larger body form called Lagania cambria entered the story too, originally interpreted as something like a sea cucumber, and later examined in ways that added still more confusion before the picture became clearer. At one point, a fossil that helped lead toward the truth was thought to be a composite, as though a jellyfish had been preserved on top of a sponge. This is exactly the sort of sentence that makes Cambrian paleontology feel less like a tidy science, and more like a slow conversation with a very eccentric rock. In 1928, another interpretation tried to fit Anomalocaris to the carapace of Tzoia, a different Burgess shale arthropod known from shell-like body coverings. That attempt also turned out to be wrong, but it shows how researchers were trying to make sense of isolated pieces by connecting them to known or partly known fossils. When you do not yet have the whole animal, you look for context wherever you can. Sometimes the context helps. Sometimes it leads you politely into a ditch. This is how science often works, though we do not always present it that way. Textbooks tend to show knowledge after the confusion has been cleaned up. A diagram appears, a label is added, a neat paragraph explains the animal. The false starts disappear, or become footnotes, but the history of Anomalocaris is valuable because the false starts are the point. They show that scientific knowledge is not simply discovered whole. It is assembled, corrected, challenged, and revised. It can take decades for the right interpretation to become visible, especially when the animal in question appears to have been designed specifically to embarrass anyone who enjoys tidy categories. By the 1960s and 1970s, the Burgess shale fossils were being re-examined in detail. Harry Whittington led a major revision of the Burgess shale material, with researchers including Simon Conway Morris and Derek Briggs contributing to the work. This was a crucial period in the reinterpretation of many Cambrian animals. Instead of treating the fossils as odd little curiosities that could be squeezed into familiar groups, researchers began studying them more carefully as organisms that might represent unusual branches of early animal evolution. This mattered greatly because Cambrian fossils often do not reward quick assumptions. Derek Briggs made an important step in 1979 when he recognised that the fossils called Anomalocaris were not whole shrimp-like animals but appendages. That was a major correction. The strange shrimp was not a shrimp body. It was a limb, a frontal feeding appendage, part of a larger animal not yet fully understood. This is the sort of reinterpretation that changes the scale of the mystery. If the fossil is only an appendage, then the whole animal must have been much larger. Suddenly Anomalocaris was not a small odd crustacean-like creature. It was part of something big, and the Cambrian Sea became a little more unsettling. The real breakthrough came in the early 1980s, when Harry Whittington was preparing an unidentified Burgess shale fossil from the Geological Survey of Canada. By carefully removing layers of rock, he revealed structures underneath. What he uncovered brought the separated pieces together. Two Anomalocaris appendages attached to the head region of a large body, along with the circular petoia-like mouth apparatus. The shrimp and the jellyfish were not separate creatures. They were parts of one animal. The puzzle did not become simple, but it finally became one puzzle. That moment is one of the great detective scenes in paleontology, though it probably involved less dramatic music than it deserves. A fossil preparer chips away carefully. A form appears. The old categories begin to shift. What had seemed like separate animals are suddenly connected by stone. The creature reveals itself not by speaking, of course, because Cambrian radiodonts were famously poor correspondents, but by placing its parts in the same slab. appendages, body, mouth, context. The fossil itself solved the argument in the slowest possible way. In 1985, Whittington and Briggs described this reconstructed animal, recognizing Anomalocaris as a large swimming predator with frontal appendages and a circular mouth. Other related forms were also reconsidered, and the broader group eventually came to be known as radiodonts. The animal that had once been a strange shrimp and a separate jellyfish became one of the most iconic predators of the Cambrian. This was not a small adjustment. It changed how scientists and the public pictured early marine ecosystems. The Cambrian Sea now had a large active hunter swimming through it, not merely a collection of small crawling creatures and misplaced jellyfish. The story did not stop there. Later research and new collections continued to refine the picture. Royal Ontario Museum collecting in the early 1990s led to the discovery of more complete specimens, and later studies reconstructed Anomalocaris canadensis with greater accuracy. Researchers continued examining its mouth parts, appendages, body flaps, tail fan, eyes, and ecology. Even once the animal was assembled, the details kept changing. That is the quiet rule of fossils. Solving one mystery often reveals several smaller ones underneath. The mouth, especially, remained a subject of revision. For a long time, anomalocaridid mouths were often imagined in a fairly standard way, like circular crushing devices made from many plates. This fed the popular idea of Anomalocaris as a trilobite crushing terror. The image was irresistible: a circular mouth like a camera shutter, spiny appendages, injured trilobites, a large Cambrian predator. It seemed almost impolite not to connect them. But later work by researchers such as Alison Daly and Jan Bergstrom showed that the oral cone of Anomalocaris canadensis differed from some related forms and was triradially organised, with 3 large plates rather than the classic 4-part arrangement often associated with petoia-like mouths. This helped weaken the older idea that Anomalocaris was simply a powerful shell crusher. That's another lovely twist. Even after scientists realised the jellyfish was actually a mouth, they still had to understand what kind of mouth it was. A mouth is not just a mouth. Its shape matters. Its plates matter. Its strength matters. Its opening matters. Its likely movement matters. A structure that looks frightening may not be mechanically suited to crushing hard shells. A mouth that looks like a ring of doom may be better for gripping, suction, or processing softer prey. The fossil does not care about our dramatic expectations. It preserves anatomy, not movie trailers. The same is true of the appendages. Once they were recognised as frontal feeding limbs, they still had to be studied as mechanical structures. How flexible were they? How far could they bend? What prey could they hold? Were the spines arranged for grabbing soft animals, sifting sediment, or handling armoured prey? Different radiodonts had different appendages, and those differences suggest different feeding styles. Anomalocaris was part of a broader radiodont diversity, not the only design in the group. Some relatives may have filtered small particles, others may have sifted sediment, others may have hunted. The group was more varied than the early giant predator image suggested. This is important because it shows how the fossil mystery unfolded in layers. First, scientists had to realise that the pieces belonged together. Then they had to understand how the whole animal worked. Then they had to compare it with related animals. Then they had to revise ideas about its diet and ecology. At every stage, the answer became more accurate and less cartoonish. Anomalocaris went from strange shrimp to disconnected oddities, to apex predator, to a specific radiodont with particular anatomical limits and ecological possibilities. Each version was closer to the animal, but none was the final word forever. There is a comforting honesty in that. Science does not become weaker because it changes. It becomes stronger when it changes for good reasons. Anomalocaris is a good example because the revisions were not based on mood or fashion. They were based on better fossils, closer preparation, improved comparisons, and more detailed studies of anatomy. The evidence changed the interpretation. The animal did not change, of course. It had been dead for around 500 million years and was therefore not available for personal development. Our understanding changed. The early mistakes also tell us something about how deeply unfamiliar Cambrian life can be. If Anomalocaris had been a mammal, even an extinct one, its parts might have been easier to identify. A tooth looks like a tooth. A leg bone looks like a leg bone. A skull looks like a skull, even if it belongs to an animal we have never seen alive. But Anomalocaris had no bones, no familiar skull, no jaw, no modern arthropod body in the usual sense. Its mouth looked like a disc. Its appendage looked like a small segmented animal. Its body was soft enough that complete preservation was rare. It belonged to a body plan outside everyday experience. This is why paleontology requires imagination, but not the loose kind. It requires disciplined imagination. You must be able to picture what a flattened fossil might have been in life, while also staying loyal to the evidence. Too little imagination, and you force everything into familiar categories. Too much imagination, and you drift into fantasy. The history of Anomalocaris sits between these dangers. Early researchers did their best with familiar comparisons. Later researchers used new evidence to move beyond those comparisons. The strange animal gradually emerged because scientists were willing to admit that the familiar answer was wrong. The fossil record itself is responsible for much of the confusion. After death, an animal's body does not usually remain politely assembled. Soft tissues decay. Scavengers disturb remains. Currents move parts. Burial compresses bodies. Mineral changes alter details. In the case of Anomalocaris, isolated frontal appendages and mouth parts were more commonly found than complete bodies in some localities. If the parts most often preserved are separated from the body, then the fossil record almost invites misinterpretation. It gives you the tools without the tool user, the mouth without the face, the predator without the outline. And yet those same isolated pieces were essential. Without them, the animal might have remained unknown. The appendages were common enough to draw attention. The mouth parts were distinctive enough to be named. Even the mistakes preserved information. A wrong interpretation is not the same as useless information. White-Eaves described the appendages. Walcott described the mouth. Their names and observations became part of the later solution. Science built on the record, even when parts of that record needed correcting. There is a gentle irony here. Anomalocaris, the predator that may have made life difficult for many Cambrian animals, made life difficult for paleontologists too. First, it hunted in the sea. Then, long after death, it hunted through museum drawers, taxonomic papers, and reconstruction diagrams, catching assumptions instead of prey. It forced scientists to rethink what they were looking at. It embarrassed tidy categories. It turned a shrimp into a limb and a jellyfish into a mouth. Not bad work for an animal with no bones, no jaws, and no schedule. The public image of Anomalocaris also changed with the science. Once reconstructed as a large Cambrian predator, it became one of the stars of the Burgess Shale. It appeared in books, museum displays, documentaries, and illustrations of the Cambrian explosion. People are drawn to it because it is strange enough to feel surprising and understandable enough to feel like an animal. We can see the eyes, the appendages, the swimming flaps, the mouth. We can imagine it moving. It is not just a fossil smear. It has presence. And the story of its discovery adds to that presence, because the animal had to be solved almost like a riddle. But it is useful not to let the solved version become too neat. Even today, details of Anomalocaris and its relatives continue to be discussed and revised. Species once assigned to Anomalocaris have been moved into other genera. Mouthpart interpretations have changed. Appendage function has been modelled. New radiodont fossils have shown a wider range of feeding styles than older reconstruction suggested. The name remains famous, but the scientific picture is alive in the way good science is alive. It can still move. That movement does not make the story unstable in a bad way. It makes it accurate to the nature of deep time. We cannot interview Anomalocaris. We cannot watch it swim beside a living trilobite. We cannot drop a soft Cambrian worm into a tank and see what happens, which is probably just as well for the worm. We rely on fossils, comparisons, physical models, and careful reasoning. Some conclusions are strong, others are tentative. The best reconstructions are not guesses thrown into the dark. They are evidence-based attempts to bring a lost animal into focus. The fossil mystery of Anomalocaris is therefore more than an amusing scientific error. It is a lesson in how difficult it is to know the deep past. The past does not arrive whole. It arrives as fragments, a print in stone, a flattened disc, a curved appendage, a trace, a layer, a slab in a drawer. Each piece is real, but each piece is incomplete. To understand the animal, scientists had to connect evidence across decades, across collections, across names, and across mistaken identities. They had to let the creature be stranger than the categories available at the time, and once they did, the Cambrian ocean changed. A shrimp became a claw, a jellyfish became a mouth, a sea cucumber-like body became part of a larger radiodont story. The animal that emerged was not a small oddity, but a major predator, one of the great symbols of early animal ecosystems. It showed that the Cambrian was not only a time of strange forms, but a time of active hunters and complex interactions. The fossil mystery did not merely reveal Anomalocaris, it revealed something about the world Anomalocaris lived in. So, picture the fossils again, not as dead objects in a cabinet but as delayed messages. One message says, here is a curved segmented limb. Another says, here is a circular mouth. Another says, here is a body with flaps. For years, the messages were read separately. Then slowly they were placed beside one another. The meaning changed. The old sea gave up a little more of its shape. The animal itself had been there all along, flattened in stone, hidden by the limits of interpretation. It waited through the rise and fall of mountains, through ice ages and warm seas, through the entire history of dinosaurs, through the arrival of humans, through museum collecting, labelling, mislabelling, and relabelling. Then, at last, the pieces came together. Not perfectly, not completely, but enough for us to see a wide-eyed swimmer with spiny frontal appendages and a circular mouth moving through the Cambrian water. And now that the mystery has been mostly untangled, the question shifts. Once a creature like Anomalocaris has been found, reconstructed, and placed back into its ancient sea, we are left with another thought. No ruler of an ecosystem lasts forever. The Cambrian ocean changed. New predators appeared. New body plans rose. Old lineages faded. Anomalocaris had once been hidden in the rocks as a fossil puzzle, but before that, it had been hidden in another kind of story, the story of how even the strongest animals of one age eventually give way to the next. Anomalocaris did not fall in a single dramatic moment. There was no last battle in the Cambrian Sea, no final chase through the water, no ancient storm that swept away every wide-eyed radiodont while the trilobites watched from the sediment with quiet relief. The end of an animal's rule is usually much slower than that. It happens through changing oceans, shifting food webs, new competitors, new prey, new climates, new chemistry, and the simple fact that a body plan which works beautifully in one world may not work forever in the next. That is worth remembering, because when we speak about the fall of Earth's first great predator, it is tempting to imagine Anomalocaris like a king losing a throne. One day it rules. The next day something stronger arrives and takes its place. Nature is rarely so tidy. It is less like a throne room and more like a very crowded kitchen where everyone keeps changing the recipe, moving the furniture, and occasionally evolving claws. Anomalocaris was successful because it fit the Cambrian sea. When that sea changed, the conditions that had made it so impressive began to shift as well. For a time, animals like Anomalocaris had an extraordinary advantage. They were large for their world. They could swim actively. They could see. They had frontal appendages for catching prey. They had a mouth suited to their particular feeding style. In a sea filled with many small animals, many soft bodies, and many early experiments in defense, that combination was powerful. Anomalocaris did not need jaws, bones, or a shark's body. It only needed to be well matched to the animals and conditions around it. But the Cambrian sea did not stay the same. No sea does. Over millions of years, ecosystems changed. Prey changed. Competitors changed. The shape of marine life became more complex. The old advantage of being a large radiodont predator did not vanish instantly, but it became less unique. Other animal groups were diversifying. Arthropods were becoming more varied. Mollusks were changing. Early vertebrate relatives were present and would eventually lead toward fish that became more important later. Cephalopods, relatives of modern squids and nautiluses, would become active predators in later Paleozoic seas. Eurypterids, often called sea scorpions, would also enter the story as powerful arthropod predators. The ocean was filling with new ways to hunt. A predator can be excellent and still be replaced. That is not failure. It is simply the cost of living in a changing world. Anomalocaris was not designed for all seas. It was shaped by one kind of ancient sea, with one set of prey, one set of competitors, and one arrangement of ecological opportunities. As those opportunities changed, the old toolkit may have become less effective. Eyes, flaps, grasping appendages, and an oral cone had once been enough to make it one of the most important hunters in the water. Later, other predators arrived with different strengths. Some had shells and arms, some had better armour, some had jaws, some had new ways of swimming, biting, hiding or feeding. And the radiodonts themselves changed too. The group did not simply disappear the moment Anomalocaris faded. Radiodonts were diverse, and different members of the group lived in different ways. Some were active predators, some were likely sediment sifters, some became suspension feeders, filtering small food from the water. This is one of the most interesting parts of their story. The relatives of a famous predator did not all remain predators. Some shifted into very different roles. By the early Ordovician, some of the largest known radiodonts, such as a Eurycassis, were not raptorial hunters like Anomalocaris, but giant suspension feeders. Instead of chasing prey with spiny limbs, they filtered food from the water, which is a much calmer dining method and probably better suited to sleep narration. This change tells us something important. The fall of Anomalocaris was not simply the collapse of a whole body plan at once. It was a transition in ecological roles. Raptorial radiodonts, the grasping predators, were dominant early in radiodont history, but later radiodont diversity became more strongly associated with other feeding styles, especially among herdiered radiodonts. That suggests the old style of radiodont predation was losing its central place. The animal group continued for a while, but the kind of dominance represented by Anomalocaris did not last. The ocean was moving on. We should be careful here, because extinction is not always easy to read from fossils. The fossil record is incomplete. Some animals may have lived in places where conditions were poor for fossilization. Some may have been rare, some may not have been found yet. A lineage can seem to vanish from the record before it truly disappeared. Paleontologists have to work with what has been preserved, and preservation is not evenly distributed. It favours certain places, certain body parts, certain conditions, and certain accidents of burial. The absence of fossils is meaningful, but it must be handled carefully, like a very old teacup with a crack in it. Still, the broad picture is clear enough. Anomalocaris itself is a Cambrian animal, famous from deposits such as the Burgess Shale. Radiodonts as a larger group were important in Cambrian ecosystems, continued into the early Ordovician, and possibly survived later in rare forms, depending on how certain fossils are interpreted. But they did not remain the top marine predators forever. By later Paleozoic seas, other groups had taken on many of the roles once held by Cambrian radiodonts. That is the quiet fall. Not a sudden disappearance beneath a single wave, but a long loss of ecological importance. Imagine the Cambrian Sea again. Anomalocaris moves through it with side flaps rippling. Its eyes detect motion. Its frontal appendages are ready. Around it are soft-bodied animals, trilobites, worms, early arthropods, and other creatures of a world still new to complex predation. In that setting, it is impressive. It is one of the animals that makes the sea dangerous. Now let time move forward, slowly. The animals around it change. Some become better defended. Some burrow more effectively. Some lineages vanish. Others appear. The water column becomes home to new swimmers. The seafloor becomes more disturbed and more complex. Food webs grow denser. The prey Anomalocaris was best suited to catch may become less available, better protected, or surrounded by new competitors. A hunter can be excellent at one kind of meal and struggle when the menu changes. That sounds almost too ordinary for such a strange animal, but ordinary pressures are often what shape the largest changes. A predator does not need to be defeated in combat. It can be edged out by hunger. It can be limited by reproduction. It can lose ground because prey becomes harder to catch. It can be outperformed by a competitor that uses less energy or feeds more efficiently. It can survive in smaller numbers for a long time and then disappear from the record without ceremony. Most extinctions are not dramatic to the animals living through them. They are a series of bad seasons, missed opportunities, fewer offspring, and smaller populations. For Anomalocaris, one possible problem was specialization. Its body was excellent for a particular kind of life. It was a swimming predator with frontal appendages and an unusual mouth. That design worked in the Cambrian, but later seas offered new challenges. Once jaws became more common among vertebrates, predation changed in a major way. A jaw is a very useful tool. It can seize, cut, crush, and hold. It can be combined with teeth of many shapes. It can be powered by strong muscles and attached to a growing skeleton. Jawed vertebrates would eventually become some of the most important marine predators in Earth history. Anomalocaris came before that world. It did not lose directly to a modern shark, of course. The timing is far too early. But the long history of marine predation moved toward toolkits very different from its own. Cephalopods also became important later. Early nautiloid cephalopods with shells and grasping arms grew into powerful predators in Ordovician seas. Eurypterids would later become major aquatic arthropod predators. These animals did not simply replace Anomalocaris overnight, but they show that the ocean was developing new large hunters. The radiodont way of being dangerous was no longer the only impressive option in town. There is also the matter of food. During the Ordovician, marine ecosystems diversified greatly. Plankton became more abundant and diverse, and that may have helped support large suspension-feeding radiodonts such as Ecological. If the available food structure shifted, then feeding styles shifted with it. A predator that chases soft prey and a suspension feeder that filters abundant plankton are solving different problems. The rise of giant filter-feeding radiodonts suggests that some members of the group found success not by holding on to the Anomalocaris lifestyle, but by moving away from it. That is almost a gentle kind of survival. The family changes its habits. The old hunter's relatives stop chasing and start filtering. They remain strange, but in a new way. Instead of the face-clawed predator, we get huge animals using specialized appendages to strain food from the water. It is as if the ancient ocean looked at radiodonts and said, "The chasing business is becoming crowded. Have you considered plankton?" And some of them apparently did. But even those later radiodonts eventually disappeared. Their group did not survive into modern seas. No living animal today is an Anomalocaris. No radiodont glides under the surface with lateral flaps and a circular oral cone. The lineage is gone. What remains are fossils, reconstructions, scientific papers, museum displays, and the slightly unsettling feeling that Earth once built a predator unlike anything now alive. That absence is powerful. It reminds us that success can be temporary even when it lasts millions of years. Anomalocaris was not a failure because it went extinct. Every species eventually ends, changes, or gives rise to something else. Extinction is not unusual in Earth history. It is the normal background against which survival looks impressive. The living world around us is made from survivors, yes, but it is also surrounded by a much larger history of vanished forms. Anomalocaris belongs to that larger history. For a time it was one of the most important predators in the sea, then it became a fossil. That is not a tragic flaw. That is Earth doing what Earth does. And there is something humbling in that. The animals that seem dominant in one age are not guaranteed a place in the next. Trilobites were once everywhere in ancient seas and now they are gone. Giant marine reptiles ruled Mesozoic oceans and now they're gone. Ammonites flourished for hundreds of millions of years and now they are gone. Dinosaurs dominated land ecosystems and most of their forms disappeared, though birds remain as their living descendants, looking out from trees with the quiet confidence of animals that survived a very difficult family history. Dominance is real, but it is never permanent. Anomalocaris shows us an early version of this lesson. It rose in a sea before fish ruled, before sharks, before large-jawed vertebrates, before many of the familiar marine predators we know today. It used the tools available to its lineage and its time. It was large, mobile, sharp-eyed and effective. Then the world continued. Other animals diversified. Food webs changed. The radiodonts shifted roles, declined and disappeared. The ocean did not stop to mark the occasion. It kept filling with new swimmers, new hunters, new shells, new arms, new teeth, new eyes. If we could watch the final Anomalocaris, we might not recognize it as the final one. It would not glow with importance. It would not swim beneath a sign reading end of an era. It would simply be an animal in the water, doing what its ancestors had done. Moving, seeing, feeding, surviving for another day if it could. The end of a lineage is only obvious from far away. In the moment, it is just life becoming less common. That thought brings us back to the fossil mystery. For hundreds of millions of years after Anomalocaris disappeared, it was not famous. It was not feared. It was not known. It was stone. Its body parts lay flattened and hidden. Its world was buried, lifted, broken and exposed. Only much later did humans find the pieces and misunderstand them, then study them again, then assemble them into one animal. In a strange way, Anomalocaris had two endings. First, it vanished from the sea. Then, much later, it stopped being a puzzle and became a predator again in the human mind. Now it occupies a different kind of ecosystem. Books, museums, documentaries, scientific debates, and quiet videos watched late at night. It no longer hunts soft prey in Cambrian water. It hunts our sense of what ancient life was supposed to look like. It catches the assumption that early animals were simple. It catches the idea that predators must have jaws. It catches the belief that familiar body plans are the natural standard. Anomalocaris is gone, but it's still useful, and maybe that is the best way to end with it. Not as a monster defeated, not as a king overthrown, not as a failed experiment. As an animal that belonged completely to its own world and then left that world behind for the rocks to remember. Its fall was not a punishment. It was a change in the sea. New animals came, new pressures arrived. The old hunter's advantages faded. The ocean revised itself, as it always has. So, dear listener, after all this time in the Cambrian water, let the old sea settle, the side flaps slow, the wide eyes fade into fossil impressions, the frontal appendages once mistaken for shrimp, rest again in stone. The circular mouth, once mistaken for a jellyfish, becomes quiet. Around it, the long history of life continues forward, through fish, forests, reptiles, mammals, birds, flowers, whales, and eventually to this moment, where you're listening from your own small place on the same very old planet. If this journey into Earth's first strange oceans has been soothing, I would be grateful if you liked the video, subscribed, or shared it with someone who enjoys calm science and ancient animals that look as if they should come with instructions. And wherever you are tonight, near the sea or far from it, awake or almost asleep, remember that the world beneath us is full of old lives that came and went long before ours began. Anomalocaris had its time in the water. We have this time here now, with the room quiet, the day softening, and the ancient ocean finally growing still.